The interaction of the antenna galaxies in the night sky is a veritable firework display, illuminating thousands of nebulae and young star clusters. It's a spectacle of unspeakable beauty. The arms of the galaxies were deformed and the cores brought close together. The impact sent out two immense jets of stars and gas, earning this celestial duo the nickname the Antennae. With a 100mm aperture, it's possible to observe the galaxy duo, which appears as a diffuse spot with no detail. When viewed through a 200mm telescope, the dual nature of the object becomes clear. Its shape takes on the appearance of a V elongated towards the west. But it's only when you use 300 to 400mm instruments that the spectacle becomes striking. The two antennae galaxies form a magnificent, asymmetrical boomerang. NGC 4038 to the north represents the brighter, more curved part, while NGC 4039 to the south is thinner. Astronomers believe that within 400 million years these two galaxies will have merged. For us, this gigantic timescale is nothing compared to the lifetimes of these stars. This collision could give rise to a larger galaxy, perhaps of the elliptical type. The nearest ultra-bright infrared galaxy is ARP 220. It is located around 245 million light-years from the Milky Way, in the constellation of Serpent. ARP 220 is the result of the collision of two galaxies that are currently merging into one. ARP 220 radiates mainly in the infrared. Most of its luminosity comes from the intensive formation of young stars, since it is a star-forming galaxy. Scientists have observed over 200 stellar clusters at the heart of this galaxy, some reaching masses of the order of 10 million solar masses. ARP 220 has an active galaxy core. This core is characterized by a compact region at the heart of the galaxy. Its luminosity is higher than average and not of stellar origin. In theory, it results from accretion by a supermassive black hole. The Whale constellation is the fourth largest constellation in the sky. Its best-known stars are Mira and Difta. Within this constellation lies the ARP 147 system, also known as the Ring Train. This pair of colliding galaxies lies 440 million light-years from Earth. The Ring Train perfectly represents the most spectacular effects of galaxy collisions. The two galaxies making up the pair are considered special galaxies in that they are neither elliptical, spiral, barred spiral, nor lenticular. They are, however, regular in shape. The two galaxies are shown, one in profile, evoking the number 1, and the other from the front, appearing to represent the number 0. Together they form a gigantic 10. This extraordinary figure in the sky is the result of an extremely violent collision. The galaxy on the left, representing the number 1, has smashed right through the galaxy on the right, representing the number 0. In the same way that a pebble emits a wave when it comes into contact with water, the collision created a wave at the point of impact. This density wave traveled outwards through the affected galaxy, colliding with the star's gas and dust as they tumbled towards the center, under the effect of an increased gravitational force. As a result of the collision, the high-temperature matter clumped together, stimulating the formation of young stars. A red spot can be seen at the bottom of the right-hand galaxy forming 0. This is probably the remnant of the galaxy's nucleus after the collision. Made up of around 50 individuals, the local group is a very modest cluster in which our galaxy, the Milky Way, lies. Nevertheless, its evolution has been as tumultuous as that of larger galaxy groupings. Based on the stigmata found on the Andromeda Galaxy, also known as M31, numerical simulations have attempted to reconstruct its past. At present, M31 is the only galaxy in the local group larger than the Milky Way. 5 billion years after the Big Bang, the local group is made up, in addition to the future Milky Way, of two rather large galaxies, one of which is 4 times more massive than the other. Their relative proximity generates a mutual attraction that brings them closer together, until they inevitably collide 4 billion years later. The merging of these two galaxies gives rise to the Andromeda Galaxy. The distances between the stars of the two galaxies are so great that another head-on collision is ruled out. Tidal forces create a gigantic trail of stars. Part of it returns towards the larger galaxy, the result of the ongoing merger, while the other part escapes the latter's grasp and gathers into two dwarf galaxies known as the Magellanic Clouds. Their speed is such that they soon find themselves close to the Milky Way. Supernovas are spectacular events marking the end of the evolution of a massive star. During these gigantic explosions, the energy released in a few seconds is comparable to that emitted by a star throughout its lifetime. The phenomena triggering these explosions vary, according to whether the star belongs to a binary system or to a single star. In the latter case, a supernova explosion will only occur if the binary system's companion star is a white dwarf. Under certain conditions, the white dwarf is gravitationally bound to its companion star, absorbing matter from the latter's surface layers. The captured material falls onto the white dwarf and heats up. When it exceeds the mass limit at which a nova is formed, nuclear reactions are set in motion until it is destroyed. In the case of an isolated star, the star itself explodes once all internal nuclear fusion cycles have taken place. Gravity then takes over, and the star contracts very rapidly. The resulting heating triggers uncontrolled nuclear reactions in the core. An explosion occurs, releasing enough energy to destroy the star. The explosion leaves behind a trace called supernova remnant. This is an expanding cloud of gas. Astronomers identify supernovas by their characteristic light curve. They exhibit a rapid increase in luminosity that lasts several days. When this luminosity reaches a maximum, it stabilizes for around 10 days. It then decreases discontinuously, followed by a steady decline. Interpretation of the light curve enables us to study the evolution and dynamics of the explosion. Because of their extreme brilliance, supernovae are one of the favorite objects of astronomy enthusiasts. And it's thanks to them that around 50 supernovas have been discovered every year since 1990. Several supernovas have left their mark on the history of astronomy. On February 24, 1987, Canadian-born astronomer Ian Shelton set out to take long-pause photographs of the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, visible from the southern hemisphere. While developing his photographs, he was surprised by the presence of a new star. After consulting several colleagues, he discovered that the star had also been seen by others. The first traces of the explosion to reach Earth were carried by neutrinos, which are difficult to detect particles emitted rapidly in very large numbers, shortly before the star's increase in luminosity. SN1987a was the first supernova explosion of the 20th century to be observed by the naked eye under optimal observing conditions. It provided crucial data for understanding the mechanisms of these stellar explosions. The general principles governing the supernova phenomenon have been confirmed. Studies clearly show that 99% of the energy emitted by supernovas is in the form of neutrinos. But for the first time in 1987, thanks to the supernova explosion, neutrino emission was observed instantaneously. When the star's core collapses under the effect of gravitation, electrons merge with protons to form neutrons and neutrinos. The latter interact very little with matter and are immediately released. Another feature of SN1987a is that the star that gave rise to it was a blue supergiant. The presence of 3 gas rings around the supernova made it possible to understand that the star had evolved from a red supergiant to a blue supergiant around 20,000 years before the explosion. This progenitor star is called SK69202, or Sandalik 69 degrees 202a. It was born 10 million years ago with a mass 20 times that of the Sun. Astronomers were surprised that it was a blue supergiant rather than a red one, as it was suggested at the time that only stars in the red supergiant stage evolved into supernovas. Today, the supernova afterglow remains the focus of numerous observations, even if the search for the compact residue has so far been unsuccessful. Thanks to numerous instruments on the ground and in space, the supernova has been observed continuously, both in terms of electromagnetic radiation and by neutrino detectors. The phenomenon occurred at a distance of around 51.4 kiloparsecs from our planet. In May 1987, it reached its maximum brightness with an apparent magnitude of around +3. Supernova 1993J occurred in galaxy M81 in 1993. It was discovered by a Japanese amateur astronomer and was one of the brightest supernovas of the 20th century. Its ancestor has been identified as a K-type supergiant star, characterized by an excess of ultraviolet light, which may be due to the surrounding hot stars or a hot binary companion. SN1572, also known as Tycho's supernova, is a supernova in the constellation Cassiopeia, 7,500 light-years from Earth. It owes its name to the Danish astronomer Tycho Brahe, who first observed it on November 11, 1572. On that day, it appeared much brighter than Venus, with an apparent magnitude of -4. It wasn't until March 1574 that its brightness dropped below the threshold of visibility to the naked eye. This supernova became one of the most famous events in the history of astronomy, since it contradicted the Aristotelian theory of the inalterability of the cosmic world. Indeed, since ancient times, the world beyond the moon had been considered unshakable. For scientists of the time, it was only between the Earth and the Moon that new celestial objects could appear. Tycho Brahe's discovery implied a new object much further away. Over the course of months of observation, he also discovered that the object had not changed position relative to the fixed stars, and could therefore not be a planet, but another star. In 1573, Tycho Brahe published his discovery, calling it a new star. This revolutionary expression turned astronomy on its head. It led to the development of better astronomical classification catalogs and improved observational instruments. The supernova's progenitor star was probably a dwarf that had drawn in matter from another companion star until it exploded. Type 1 supernovas, like SN1572, do not involve the formation of extraordinary nebulae. That's why its faint afterglow was only discovered in the 1960s. Thanks to the Chandra Space Telescope, astronomers were provided with astonishing images of Tycho's supernova. These showed lumps in the remains of the star, as if several ignition points had existed within the supernova. The explanation is that SN1572 underwent an asymmetric explosion. The explosion produced a large cloud of expanding debris. A thin blue line, representing ultra-high energy electrons, can be seen around the perimeter. The dust formed is ejected into the cosmos. Numerous other stars adorn the supernova's vicinity, like sparkling white diamonds. SN1604, also known as the Kepler supernova, occurred in the Milky Way in the constellation of Ophiuchus in 1604. It is a type 1a supernova, or thermonuclear supernova, resulting from the explosion of a white dwarf. In most cases, the latter captures the matter of a companion star until it reaches critical mass and explodes. In the case of Kepler's supernova, however, it appears to have been triggered by the merging of two white dwarfs. As there are no bright stars in the vicinity of the central region of the supernova's remnants. SN1604 was observed by German astronomer Johann Kepler and was visible to the naked eye for over a year. Kepler was not the discoverer of the supernova, but it was he who carried out the most detailed research on the star. He wrote about it in his book, Sur la nouvelle étoile dans la pied de Ophiuchus, On the New Star in the Foot of Ophiuchus. This supernova lies at a distance of 20,000 light-years from our planet Earth. Its relatively low position on the horizon and declination of -21 degrees could have made it difficult to detect, but certain circumstances were favorable to its discovery. SN1604 lies in a region where the planets of the solar system circulate. In October of that year, Jupiter, Mars, and Saturn were located in this very zone. What's more, with the Sun at the same time located around 60 degrees west of this region, the sky was easily observable in the early hours of the night. What's more, Tycho Brahe's discovery some 30 years earlier had sparked a great deal of interest among astronomers in observing the night sky. Today, NASA astronomers report that some debris from the explosion is still moving through space at speeds of up to 37 million kilometers per hour. The average speed of the clusters studied is around 16 million kilometers per hour. The four fastest clusters in SN1604 are all heading in the same direction and have a similar chemical composition. This may mean that the debris is coming from a single layer of the progenitor star. These velocities have already been observed in supernovae and other galaxies, but only just after their explosion. In the case of SN1604, the displacement of its remnants continues unabated, even 400 years later. Astronomers have yet to explain this phenomenon, but several theories have been suggested. The explosion could have been so violent that the material was ejected at very high speed, or the white dwarf's environment is lumpy and the debris made its way along low-density paths without being slowed down. SN1054, also known as a supernova of the year 1054, is famous for the afterglow it left behind after the explosion, known as the Crab Nebula. It is one of the most studied objects in the sky. The supernova was observed in 1054 and documented by Chinese and Arab astronomers. Numerous written sources attest to the explosion of a star in 1054. At the time, in China, transient stars such as comets, novas, or supernova explosions were called guest stars. Several accounts in official archives of events during certain dynasties relate this phenomenon in 1054. 3 other Japanese texts, individual chronicles, also mention this guest star at the same time. In the Arab world at the time, astronomers were interested in cyclical phenomena, whereas supernova explosions were considered to be atmospheric phenomena. Nevertheless, there is a doctor's account of a spectacular star appearing in the sky. All report that in July 1054, a star began to shine so brightly that it exceeded the brilliance of Venus. It remained visible in daylight for 3 weeks, and in the night sky for almost 2 years. 7 centuries later, in 1758, the famous Charles Messier searched assiduously for Halley's Comet and confused it with a small nebula in the Taurus constellation. To avoid further confusion, he decided to create a catalog of diffuse stars and assign the number 1 to this star. In 1928, Edwin Hubble made the connection between the Chinese astronomer's guest star and the Messier 1 nebula, the expanding cloud of gas released by the supernova of 1054. It's nicknamed the Crab Nebula. This nebula continues to grow at a speed of 1,500 kilometers per second, or 930 miles per hour, and will dilute in space over the coming millennia. Within the nebula remains the compact residue of the exploded star, the Crab pulsar. The pulsar is less than 1,000 years old. It generates electromagnetic radiation 100,000 times more intense than the Sun. This is what makes the central part of the Crab Nebula so bright. The nebula and pulsar form one of the most studied structures outside the solar system, as both are among the brightest objects in their respective categories. What's more, the date of the explosion is well known. SN 1054 is the most famous supernova in the history of astronomy. In winter in the northern hemisphere, it can be observed through a small telescope and appears as a pretty gray blob against the stellar background of the Milky Way. Supernova 2014J occurred in galaxy M82 in January 2014. It is a Type 1a supernova, and the closest to it discovered in over 40 years. To date, it remains the brightest supernova observed in the Cigar Galaxy for decades. It has been extensively studied in different wavelengths due to its unusual brightness and proximity. Far less spectacular than Type 2 supernovas, which are the endpoint of massive stars, whose remnant is usually a neutron star, Type 1a supernovas are produced by the explosion of much smaller stars, known as white dwarfs. Their explosions are said to be thermonuclear. At the end of the explosion, all that remains in space is a gigantic jet of particles known as afterglow. The supernova was discovered on January 21, 2014 by chance, while astronomer Steve Fosse was training his students to use a small telescope at the University of London Observatory. The scientists simply wanted to take advantage of a brief gap in London's cloud cover. He and his students then noticed a bright new star in the images taken of the Cigar Galaxy. The discovery was reported to the Astronomical Union's Central Astronomical Telegram Office, which confirmed that they were the first to spot this supernova. At the time of discovery, the supernova was 14 days from its maximum light, suggesting that it would become brighter over the following 2 weeks. It continued to get brighter until January 31st, when it had an apparent magnitude of 10.5. Quasars are the brightest sources of light in the universe. The word quasar comes from an English abbreviation meaning source of quasi-stellar radio radiation. These are extremely distant stars that look like very bright stars when observed through a telescope, but are actually examples of active galactic nuclei. Their impressive energy comes from the accretion of matter by rotating supermassive black holes that can contain millions to billions of solar masses. The black holes that sit at the center of galaxies are of an altogether different caliber to those produced by stars. While the latter sometimes reach the mass of the Sun, galactic black holes are millions, even billions of solar masses. The luminous power emitted by quasars can reach 10,000 times the total luminosity radiated by the hundreds of billions of stars in a galaxy the size of our Milky Way. However, most galaxies are not the site of such a violent outburst. Quasars are thought to gain power through the accretion of matter around supermassive black holes in the nuclei of these galaxies. No other mechanism seems capable of explaining the immense energies released and their rapid variability. But some phenomena remain unexplained to this day. For example, some relatively quiet galaxies seem to suddenly become quasars in just a few months. The remarkable luminosity of quasars is used as a tool for probing intergalactic space right up to the limits of the observable universe. Before reaching our telescopes, the photons emitted by quasars may encounter tenuous clouds of intergalactic gas on their billion light-year journey. Quasar absorption systems provide additional structural information to that provided by the distribution of galaxies. The growing number of known quasars, with their absorption spectra, enables more detailed statistical studies of the distribution and properties of intergalactic gas clouds and their relationship with dark matter and existing or forming galaxies. Absorption systems can be used to probe precise moments distributed throughout the history of the universe, but also to address essential issues in cosmology and even physics. The first quasars were seen as early as the late 1950s, and today there are over 100,000. Quasar 3C273 lies at an astronomical distance of 2.44 billion light-years, 1,000 times further away than the Andromeda Galaxy. It is located in the constellation Virgo. According to Hubble's law, and given its distance, this quasar is moving away at almost 50,000 kilometers per second, or 31,000 miles per second. The black hole at its center needs the equivalent of several hundred times the mass of the Sun per year to feed itself. It discharges some of this matter in the form of an immense jet. When it no longer has enough energy to feed itself, its host galaxy will revert to an ordinary star, and its luminosity will diminish. If there's one object in the universe renowned for its unprecedented violence, it's the Quasar 3C186. This double quasar emits waves in all domains of light. It lies in the Lynx constellation, more than 8 billion light-years away. 3C186 lies at the heart of the galaxy, PGC 2817581, It has several special features. Its central light is offset by around 35,000 light-years from the center of the galaxy. This is due to the interaction between 3C186 and the second black hole inside it. The impact of these two supermassive black holes disrupts the galaxy, breaking it up and scattering its stars. The interaction between the two black holes is thought to have taken place 5 million years ago. Astronomers estimate that 3C186 will leave the galaxy in around 20 million years. The result will be two supermassive black holes merging to form a black hole with a mass equivalent to 1 billion solar masses. The Earth has been hit by numerous asteroids. These collisions have played a major role in the history of its formation and evolution. Some 9 billion years have passed since the Big Bang. The local supercluster contains over 10,000 individuals. On its periphery, the local group is made up of some 50 galaxies, including the Milky Way, one of the largest. The Milky Way has a thin disk of stars and gas. This highly diluted gas concentrates in a few places, in much denser spirals. These interstellar clouds are opaque with molecules and grains of dust. One of them wanders proudly 27 light-years from the center of the Milky Way. Then, a fragment of this nebula collapses in on itself. The contraction transforms the globule into a protostar, and its energy into radiation. At its heart, the temperature rises so high that thermonuclear reactions cause hydrogen to fuse. A star is born, but not just any star, our Sun. Before its final contraction, the protostar is surrounded by a disk of gas and dust, which then divides into countless smaller bodies. Some agglomerate into larger structures. Matter spinning too fast to join the Sun in formation takes the form of a disk made up of gas, dust grains, and tiny aggregates of solid matter. The grains gradually stick together until they agglomerate into blocks. Under the effect of gravity, bodies over 1 kilometer in length are formed. The largest of these absorb everything within their sphere of influence. Planetary embryos are born. Their mass increases with distance from the Sun. Below the ice line, the environment is gradually emptied of gas, and the planetary embryos see their orbits lengthen to the point where they can cross each other. Violent collisions ensued, leaving only 4 of the planets, including Earth, intact. Barely scratched out of the ground, the Earth is already experiencing an eventful life. Our planet has cleaned up its orbital zone. The only exception is the 2 Lagrange points, L4 and L5, in the Earth-Sun system, which provide shelter for planetesimals attracted to the Earth during its formation. Point L4, for example, shelters a planetary embryo that continued to develop until it reached the size of today's Mars. Its name is Theia. Having reached too great a mass, Theia became unstable and escaped from its L4 equilibrium point. It then orbits the Sun until it collides with the Earth. Theia is totally shredded. Its pieces scatter all around. Its core, mainly iron, is buried in the heart of the Earth. 24 hours after impact, our future planet is surrounded by a disk of light rock from the 2 planetary mantles that collided. After a few years, these rocks agglomerate to form a new celestial object 20,000 kilometers or 12,500 miles from the Earth, which gradually moves away to become its satellite, the Moon. At first glance, this cosmic collision seems no more exceptional than any other. And yet, By giving the Earth such a large satellite capable of stabilizing its axis of rotation, this collision is paradoxically an essential event in the future evolution of life. The Moon plays a very important role in the existence of life on Earth. It exerts a major influence on the weather, the migrations of certain animals, the Earth's magnetic field, and in many other areas. It is also responsible for the 24-hour day. The Earth's tilt is kept stable by the Moon's gravity. If it weren't for the Moon, our planet would move up and down during its rotation. And if such wild movements were to take place, wind and clouds would move faster, and weather conditions would be extremely harsh and much less conducive to life. The phenomenon of the 4 seasons is also due to these changes in the Earth's rotation and axis. Without the Moon, the Earth would rotate on its axis in 8 hours instead of 24. The Moon's gravity slows down the Earth's movement, with enormous repercussions for the evolution of life on Earth. If a day lasted 8 hours, animal species would have had to adapt to rapid temperature changes and would certainly have evolved very differently. During the Moon's first days, solar winds were much more violent. At that time, the Moon was closer to the Earth, and its magnetic field was sufficient to protect its atmosphere and act as a shield against solar winds. If the Earth had no atmosphere, life as we know it today would not be possible. It contains the oxygen we breathe and protects us from ultraviolet rays and cosmic rays. The effect of the Moon's and Sun's gravity on the Earth slightly deforms the planet from front to back. This is what we call tidal forces, which cause ocean tides. Tides probably propelled the first forms of marine life onto land. Tides may also have influenced the Earth's plate tectonics. It is thanks to seismic activity that the planet's surface was able to cool and become habitable. "4 billion years ago, large-scale meteoric and cometary impacts hit the terrestrial planets. It was during the Apollo 15, Apollo 16, and Apollo 17 missions that this theoretical period in the history of the solar system was brought forward. The landing sites for these missions were established close to the great impact basins of the Sea of Rain, the Sea of Nectar, and the Sea of Serenity. Lunar rock samples were collected, and analysis on Earth revealed that their age ranged from 3.8 to 4.1 billion years, a relatively short period. These data were compared with the dating of other lunar meteorites recovered on Earth. Due to erosion, impact marks of ancient origin are very rare on our planet. Although this has long been interpreted as proof that the Earth's surface remained liquid for a long time, it would appear that in reality, the solidification time was much faster, and that the youth of the Earth's crust is due to the theory of the late Great Bombardment. At the start of the solar system's formation, the 4 giant planets were much closer together than they are today. Uranus is the furthest from the Sun, and lies close to the inner edge of a planetesimal-rich disk. Barely 600 million years after the formation of the solar system, the gas giant planets began to migrate due to gravitational interactions with the famous small objects that remain at the inner edge of the disk. Saturn, Neptune, and Uranus are moving strongly inwards, and Jupiter more moderately. Jupiter's rotation period around the Sun is half that of Saturn. This movement completely destabilized the solar system, and collisions between small bodies and the terrestrial planets increased. It was the beginning of chaos. Saturn was pushed back into its final orbit by Jupiter and collided with Neptune and Uranus. The latter two are expelled into much more elongated orbits. They plunge into the planetesimal-filled disk, ejecting thousands of planetesimals far from their original orbits. For the most part, these small bodies fly outside the solar system, giving rise to the Kuiper Belt, among others. But some of them head inland. The 4 terrestrial planets, as well as the Moon, are the victims of numerous brutal impacts. The Earth is said to have been hit by 22,000 giant meteorites. Some asteroids were larger in diameter than France. The oceans that covered the Earth's surface were partially vaporized. Mercury, the Moon, and Mars bear the scars of this massive bombardment. On Mars, the Hellas Planitia impact basin has been linked to the Great Lake bombardment by analysis of lunar samples. The basin measures around 2,200 kilometers, or 1,400 miles in diameter, and 9,500 meters, or 31,000 feet in depth. It is the largest impact structure on Mars visible from Earth. The basin appears as a bright area due to the high albedo of the dust constantly stirred up by the winds. The Hellas Planitia basin is surrounded by relief created by the impact. For over 1,000 kilometers, the terrain was raised. To the west, the edge of the basin is marked by a mountain range. In places, it reaches an altitude of 2,000 meters or 6,500 feet. To the east, the edge is marked by valleys, representing the beds of large rivers that have now dried up. Water was abundant in the impact basin. On the planet Mercury, the Caloris Basin is the most massive meteor crater known to date. It is located at one of the planet's 2 hot poles. Measuring around 1,550 kilometers, or 960 miles in diameter, it was formed by the fall of an asteroid with a diameter of around 150 kilometers, or 93 miles. The basin is surrounded by mountains that rise to almost 2 kilometers, or 1 mile in height. Its floor is filled with cooled lava, reminiscent of lunar pools. For some 1,000 kilometers or 620 miles, the material ejected by the impact forms rings surrounding the basin. The impact that formed the Caloris Basin is thought to have triggered volcanic activity on Mercury. The impact is also thought to have released heavy elements such as sodium and potassium from the planet's mantle. Being around 130 kilometers or 80 miles deep, elements could have been brought up from the mantle during readjustment movements. On the Moon, the Mer Orientale and the Mer des Pluies are basins that would also have been dug during the Great Lake bombardment. The Mer Orientale is a lunar sea formed by the impact of a meteorite, which raised the mountains bordering the crater. It is one of the Moon's most impressive structures, with a diameter of around 900 kilometers, or 560 miles. 2 mountain ranges encircle the Mer Orientale. The Montes Rook, measuring 700 kilometers, or 430 miles in diameter, and the Montes Cordillera, measuring 900. The Sea of Rains is a sea found on the visible side of the Moon, formed when liquid lava filled a giant pre-existing impact crater, called the Basin of Rains. The latter is surrounded by 3 mountain rings, each composed of several mountain ranges. For some 800 kilometers or 500 miles, an area is covered by ejecta, forming a region of numerous reliefs. Asteroid impacts are common phenomena in the solar system. 160 million years ago, a collision between 2 large objects in the asteroid belt produced numerous fragments, known as the Baptistina family. The first body is located on the inner edge of the asteroid belt, just over 2 astronomical units from the Sun. Despite the fact that its growth is limited by the disruptive presence of Jupiter, it boasts a diameter of 170 kilometers or 100 miles, a very respectable size. It is one of the largest asteroids in the main belt. The second body involved in the collision is another asteroid, 60 kilometers or 37 miles in diameter. Its orbit is similar to that of the first asteroid. One day the two collide. The impact occurs at a speed of 3 kilometers per second, or 1.8 miles per second. It was so violent that the two asteroids were reduced to a dust of debris, which aggregated again to form a family of objects with similar orbital characteristics. This is the Baptistina family. This asteroid family comprises some 2,500 known members. Many years ago, we thought that some of them were responsible for remarkable cosmic collisions, such as the one that caused Tycho's crater on the Moon, or a direct collision with the Earth 66 million years ago. However, data from the Wide Field Infrared Survey Explorer in 2011 challenged this hypothesis, suggesting that the Baptistina family had in fact formed much more recently than previously thought, as recently as 80 million years ago. Consequently, the origin of the impactor that caused the extinction of the non-avian dinosaurs remains an unsolved mystery. Further study and exploration of the asteroid belt may one day unravel this mystery and help us understand the forces at work that triggered these impacts. Asteroids can undergo an effect that affects their rotation on themselves in the presence of radiation. When the object's face is illuminated by the radiation source, it receives energy. After half a revolution, this same face then goes into shadow, radiating outwards the energy it has previously received. The result is a very slight thrust exerted on the object, depending on its shape and surface condition. This is known as the Yarovsky Effect, named after the Russian engineer who discovered the phenomenon. Many individuals are then disrupted by Jupiter and the other planets. They find themselves injected into orbits that lead them to cross those of the Earth and Moon. 108 million years ago, an asteroid measuring 10 kilometers or 6 miles in diameter swung low over the Moon's western horizon and collided with it. The impact creates a huge impact crater called Tycho. This sends thin cracks across the Moon's southern hemisphere, extending to over 1,000 kilometers or 620 miles in all directions. The crater is located in the southern lunar mountains. It has well-defined contours, and its interior is characterized by a high albedo. The crater's diameter is 82 kilometers or 50 miles, and its rim rises to 4.7 kilometers or 3 miles above floor level. At that time, from Earth, it was the dinosaurs who witnessed this cosmic collision. Little do they know that they will be the next victims of these cosmic events. The Chicxulub Crater is the most famous asteroid impact on Earth. It occurred around 66 million years ago in Mexico's Yucatan Peninsula and is associated with one of the world's largest mass extinctions. The impacting asteroid measures around 10 kilometers in diameter. On contact with the Earth, it formed a crater 180 kilometers, 112 miles in diameter. This suggests an explosion power several billion times that of the Hiroshima bomb. The crater basin is covered by about 1,000 meters or 3,300 feet of limestone. It extends under the mainland and the Gulf of Mexico. Scientists are trying to explain what really happened during the impact that caused the demise of those who reigned supreme at the time, the dinosaurs. At the time, these gigantic, majestic animals had dominated the planet's animal ecosystem for 165 million years. They are the most imposing creatures the Earth has ever sheltered. Dinosaurs are very diverse and are found all over the planet. An asteroid in a region between the orbits of Mars and Jupiter is projected at several kilometers per second. It heads straight for the Earth until impact, forming a huge crater. The energy released was so intense that the rock of the Earth's crust liquefied. In less than a second, all the water within a 60-kilometer radius of the impact turns to steam. Animals in the vicinity are instantly killed. A few seconds after impact, the shock wave releases an unbearable heat that crosses the ocean. Everything in its path evaporates or melts. It would take just a few years for life to reappear in the impact crater, but over 30,000 years for a thriving ecosystem to develop. Scientific research has revealed the presence of burrows dug by shrimps and worms, as well as microfossils of plankton and algae. This suggests that the crater became habitable shortly after impact, even though the mass extinction was not yet over. Evidence of this impact was confirmed just before the 1980s. A thin black layer of clay just a few millimeters thick was revealed in some of the geological layers between the Cretaceous and Tertiary strata. This geological boundary contains abnormal levels of iridium. Although rare on Earth, iridium is found in abundance in certain meteorites. Scientists sometimes find minute quantities of iridium in terrestrial sedimentary rocks due to the fine, micrometeorite showers that are frequent on the planet. But analysis of this Cretaceous Tertiary layer reveals far more. This is why it has been suggested that the planet must have suffered the fall of a huge meteorite. At the time, the crater could not be found. In 1981, two geophysicists employed by the Mexican oil company Petróleos Mexicanos investigated the Yucatan and discovered this unusual geological structure. The fall of this meteorite marked the end of the Cretaceous period and was responsible for a climatic upheaval that led to the extinction of non-avian dinosaurs and a large proportion of the animal and plant species at the time, both on land and in the seas. Without this event, Earth's history would be totally different, and we certainly wouldn't be here to talk about it. The Verafort Dome is the largest known impact crater on Earth. It is located in South Africa, in the territory of the Free State Province. In 2005, Verafort Dome was inscribed on UNESCO's World Heritage List for its scientific and scenic interest. The town of Verafort was built inside the impact crater. The asteroid's impact dates back 2 billion years. Until recently, it was the oldest known impact crater on Earth, until the discovery of Manco Crater in Greenland, estimated to be 3 billion years old. The asteroid's diameter has been estimated at 15 kilometers or 9 miles. It left a crater with a diameter of around 300 kilometers or 186 miles. Verafort is one of the few craters to feature multiple terrestrial rings, a phenomenon often destroyed by erosion and plate tectonics. The dome is only the central part of the astrobleme, which actually extends over 360 kilometers or 224 miles in length, from Johannesburg to Welcome in the Free State. South Africa's geological stability has ensured the crater's continued existence. It is one of the only craters to have been crossed by a river, the Vaal, for almost 280 million years. The asteroid's impact would have really damaged the planet, causing fires all over the world. The enormous quantity of dust thrown into the atmosphere would have altered the climate for years. Located in Ontario, Canada, the Sudbury Basin is a crater formed some 1.85 billion years ago. It is the second largest known impact crater on Earth, but also one of the oldest. It is located on the Canadian Shield in the city of Greater Sudbury. The Sudbury Basin is 62 kilometers or 39 miles long, 30 kilometers or 19 miles wide, and 15 kilometers or 9 miles deep. The diameter of the meteorite has been estimated at around 10 kilometers. Some of the rock fragments ejected on impact traveled more than 800 kilometers, or 500 miles, and were scattered over an area of 1.6 million square kilometers. Scientists even suggest that such an impact may have scattered debris around the world, but that it has since been eroded away. The impact that created the Manco Crater is thought to have occurred around 3 billion years ago. It is the oldest known terrestrial meteorite crater, yet remains totally invisible today due to erosion. By analyzing the nature of the rocks, scientists were able to prove that it was an asteroid impact. The asteroid would have had a diameter of around 30 kilometers or 19 miles, and would have hollowed out a crater, originally 600 kilometers or 370 miles in diameter. At the time, only bacteria were beginning to populate the planet, but if such an object hit us today, it would exterminate all forms of life on Earth. Also known today as Meteor Crater, Behringer Crater is located in Arizona, USA, 60 kilometers or 37 miles east of Flagstaff. It is a well-preserved crater formed by the impact of a small asteroid around 50,000 years ago. At the end of the Pleistocene, an object of peculiar composition hurtled towards the Earth. Made of iron and nickel, it is more likely to be a fragment of a planet core in the process of forming than a small body from the early solar system. As a result, it is much more resistant to the stresses imposed by the Earth's atmosphere than blocks of rock or ice. Once it reaches an altitude of around 14 kilometers or 9 miles, it eventually breaks up under the effect of increasingly dense layers of air. The meteorite splits into two parts, with a block of half its initial mass on one side and smaller fragments surrounding the initial impact over a diameter of 200 meters or 660 feet on the other. The main block, weighing 300,000 tons, hits the Earth at a phenomenal speed at 12 kilometers per second or 7 miles per second. The collision forms a crater over a kilometer in diameter. At the time, this area was grassy savanna occupied by mammoths and sloths. The impact releases energy equivalent to that of a thermonuclear explosion. All life is destroyed within a radius of several kilometers due to the blast and heat generated by the collision. The impact did not cause any noticeable change in the planet's climate. Meteor Crater is bowl-shaped, measuring almost 1,400 meters or 4,500 feet in diameter, and 190 meters or 620 feet deep. Today, it is a popular tourist attraction. Warburton Crater is located in Australia near the town of Ora Banda. Its diameter is around 5 kilometers or 3 miles. The asteroid's impact is thought to have taken place 100 million years ago during the Cretaceous, well before the impact that formed the famous Chicxulub Crater. The Warburton Crater was discovered in a very flat landscape. Erosion has taken its toll, and there's no sign of a crater on the surface. The impacting asteroid must have been between 100 and 200 meters in size, or between 330 and 660 feet in diameter. The crater is buried under several kilometers of sediment. It is not a single impact crater, but two craters, 200 kilometers or 125 miles wide, forming a structure 400 kilometers or 250 miles in diameter. The two impacts may have occurred simultaneously due to the fragmentation of an asteroid. The Populated crater is located in Siberia. It is the fourth largest known terrestrial impact crater, with a diameter of around 100 kilometers. It was formed by a meteorite impact 35.7 million years ago, during the Upper Eocene. It has been designated a geopark by UNESCO as a site with a specific geological heritage. Populated is also the world's largest diamond mine. During the Cold War, it was kept secret for decades. Shock waves from the impact would have instantly transformed graphite into diamonds within a radius of 14 kilometers or 9 miles. This mine would contain the equivalent of 10,000 billion carats. Just over 200 million years ago, an asteroid hit the north shore of Quebec in Canada, forming the Manco Crater. It is one of the oldest and largest impact craters on the planet. Due to erosion caused by glaciers, it is not easily visible on the Earth's surface. Its concentric structure, around 100 kilometers or 62 miles in diameter, is explained by the shock waves transmitted during the impact. The meteorite responsible measured around 5 kilometers or 3 miles in diameter. Comet Shoemaker-Levy, sometimes abbreviated SL9, is famous in astronomy for being the first to offer direct observation of a collision between two solar system objects outside the Earth. It has been closely observed by astronomers from all over the world. Comet Shoemaker-Levy broke up as it approached the planet Jupiter, colliding with it in July 1994. This collision led to the discovery of new elements about Jupiter and highlighted its key role in reducing the amount of space debris in the solar system. This comet is unusual in that it has been orbiting Jupiter for some time, rather than orbiting the Sun, like all the other comets known at the time. By 1992, it had already passed very close to Jupiter, just over 40,000 kilometers or 25,000 miles from the cloud tops. The 1994 collision was by far the closest and resulted in the comet's fragmentation. Each fragment is designated by a letter, ranging from fragment A to fragment W. The 1994 encounter was eagerly awaited. Astronomers had prepared their terrestrial telescopes, and several space observatories were ready to observe the impact live. On July 16, 1994, at just over 8 p.m., Fragment A struck the southern hemisphere of Jupiter at a speed of around 60 kilometers per second, or 37 miles per second. A fireball then formed. A fireball was formed reaching a temperature of around 24,000 degrees Celsius, or 43,000 degrees Fahrenheit, before dropping rapidly to around 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. After this initial impact, observers see a huge black spot. These were the effects of impact debris. Over the following week, 21 impacts were recorded, the largest of which was produced by Fragment G. It took place on July 18th at around 7:30 a.m., creating a giant dark spot over 12,000 kilometers or 7,500 miles wide. On July 22nd, the final fragment, Fragment W, struck Jupiter. Direct observation of this collision provided a wealth of information about Jupiter. The planet has since been regarded as a kind of cosmic vacuum cleaner within the solar system. Jupiter's strong gravitational influence attracts numerous small comets and asteroids. Its impact rate is estimated to be between 2,000 and 8,000 times greater than that of our planet. In other words, if it weren't for Jupiter, asteroid impacts on the other planets in the solar system would be far greater. Astronomers have even gone so far as to hypothesize that without Jupiter to intercept potential impacts, collisions leading to mass extinctions, such as the cosmic impact that caused the Chicxulub Crater, would be much more frequent, and Earth would certainly not have been able to witness the development of complex life forms. In 2018, astronomers discovered the first isolated neutron star outside the Milky Way. They detected it while observing the Small Magellanic Cloud, 200,000 light-years from our Sun, and more precisely, the remains of a supernova explosion that occurred there almost 2,000 years ago. This discovery was made possible by the use of advanced technology. By superimposing the X-rays captured by NASA's Chandra Space Telescope with the visible light observed by the MUSE instrument, mounted on the European Southern Observatory's Very Large Telescope in Chile, they were able to immortalize the remains of this cataclysmic event. In this fabulous pocket of gas, named E0102 and known for almost 35 years, they detected a second ring of gas. This one, much smaller in size, shelters a bright spot in X-rays, a neutron star. While the scientists weren't too surprised by their find, they were stunned by its characteristics. The star is surrounded by two gaseous rings, both highly asymmetrical and extending at different speeds. The main ring expands at a speed of around 1,000 kilometers per second, or 620 miles per second, while the smaller ring, that mainly houses the star, has a speed of around 90 kilometers per second, or 56 miles per second. Scientists are comparing the energy spectrum of this neutron star with that of two other well-known stars in our galaxy. These are located in the supernova remnants Cassiopeia A in the constellation of the same name, and Puppis A in the constellation La Pope, also unaccompanied by another star. The star, detected only by its X-ray emissions, emits no radio emissions, pulsed or otherwise, indicating that its magnetic field is relatively weak. Of all the neutron stars discovered to date in the Milky Way, only 10 others display these same characteristics. But what is of great interest to astronomers is to understand how this neutron star came to be so far from the center of the main ring, and why it is moving, albeit slowly. Astrophysicists are studying two scenarios. It could be a displacement or deformation of the vast shock wave following a series of precise circumstances leading to this asymmetry. Alternatively, it could be that the neutron star, rather than the gas pocket, underwent a sudden impulse after a strong, asymmetric explosion, propelling it to its present position. In short, this first extragalactic neutron star, although in the spotlight, has not revealed all the secrets surrounding the circumstances of its violent death. Let's take a closer look at the puzzling characteristics of neutron stars. These stars are exceptionally small, averaging just 20 kilometers or 12 miles in diameter. On the other hand, their density is extraordinarily high, estimated at nearly 1,000 billion tons per liter. By way of comparison, if a teaspoon of this class of star were brought down to Earth, it would weigh over 1 billion tons. That's why they're often referred to as the relics of all extremes. What's more, these stars have a particularly intense magnetic field. It's usually on the order of 100 billion teslas, the tesla being one of the units of measurement for magnetic fields. When you put it like that, I imagine you'll find it hard to imagine what this represents, which is normal. In fact, the magnetic field of a neutron star can be described as immeasurable, especially when compared to that of our planet. The magnetic field of a neutron star is on average 100,000 billion times stronger than that of the Earth. There's another surprising feature of neutron stars. Their surfaces are particularly smooth, devoid of any irregularities. This is all the more disconcerting, given that such dense objects generally exhibit extraordinary gravitational attraction, which has repercussions on their surface relief. A study of the prominences observed on the surface of neutron stars estimates that their highest peaks are less than 1 millimeter high. Proportional to the Earth, the tops of these mountains would not exceed 50 centimeters or 20 inches. With such a force of gravity, it goes without saying that life is impossible on the surface of such an object, which, although it bears the name of a star, is technically no longer one. Indeed, to be scientifically perceived as a star, it would still have to be capable of stellar nucleosynthesis. However, neutron stars no longer have the necessary resources, and are therefore considered to be dying stars. By the way, what is a neutron star made of? Like all stars, it has a multi-layered structure with varying densities. Let's start by dissecting the star's anatomy, by looking at its atmosphere. This is reduced to a thin gaseous envelope whose thickness can be calculated in centimeters. This first layer, sometimes referred to as a gaseous ocean, has a temperature of several million degrees. Gravity at its surface is 10 billion times greater than that of the Sun. Oddly for a star, this first envelope conceals a solid surface. This is the outer crust, similar in composition to the interior of a white dwarf. Composed essentially of iron, it contains highly ionized atomic nuclei and free electrons. The iron atoms form a sort of latticework, creating a crystalline structure. As density increases, fusion reactions between atomic nucleus protons and free electrons create protons. The result is a transmutation of the basic atomic nuclei, which then resemble nickel, zinc, or krypton, depending on their density. When the density becomes too great, the nuclei, themselves too rich in neutrons, let some of the latter escape into what is known as the inner crust. The inner crust is made up mainly of extremely neutron-rich nuclei, bathed in a gas of neutrons and free electrons. The entire outer layer, divided as we've just seen into two zones, is around 1 kilometer or 0.6 miles thick. Below this limit, the density becomes so great that the atomic nuclei have completely disappeared, gradually dissolving. All that remains is a superfluid neutron soup, mixed with a small quantity of protons and electrons. This zone, approximately 10 kilometers or 6 miles in size, corresponds to the outer core of the neutron star. As the proton gas is superconducting, it must play a key role in the magnetic field. We're now at the heart of the neutron star, which could be in the form of a solid core. Of course, this is only a hypothesis, as this inner part of the star is not accessible, and therefore not observable. However, certain characteristics of this precise part of the star can be estimated, notably by studying its mass and/or radius. For example, a neutron star with a radius of around 10 kilometers or 6 miles and a mass equivalent to 1.4 times that of the Sun would have a solid inner core 1 kilometer or 0.6 miles in diameter, where the neutrons would form a crystalline structure. It remains to be seen how the particles that make up the neutrons and protons, namely the quarks, reorganize themselves into this extremely dense environment. Do they form hitherto unknown combinations? Another peculiarity of neutron stars is their rotation speed. They generally have a rotation period measured in seconds. For some, this speed can be 30 seconds, while the most excessive ones rotate in just 1/100th of a second. To explain this more or less frenetic pace, scientists suggest that the neutron star, at the moment of its creation, recovers the rotational motion that the star previously possessed, conserving its angular momentum, also known as angular momentum. As a result, as the neutron star contracts, becoming smaller and smaller in size, its rotational speed can only increase. Since a star's motion is proportional to its mass, radius, and angular velocity, what would happen if our Sun were to turn into a neutron star? Its current radius, around 700,000 kilometers, would be reduced to just 15 kilometers or 9 miles. With its mass maintained at the same level, i.e., nearly 333,000 terrestrial masses, our Sun's speed would increase exponentially. If it currently takes 25 days to complete one rotation, it would then rotate. Hold on to your hat, at 1,000 revolutions per second. Although this example is very explicit, it will never become reality. The Sun isn't massive enough to pretend to end its days as a neutron star. It will turn into a banal red giant and end up as a white dwarf. A priori, all neutron stars rotate rapidly after formation. However, this speed tends to decrease as the star's magnetic field dilutes its energy. As a result, an older neutron star will rotate more slowly than a newer one. It seems that the observed rate of decrease in rotation speed is relatively constant, and above all, insignificant. Depending on their behavior, neutron stars are classified into several subcategories. Some of these stars stand out in more or less extraordinary ways. Let's take a look at magnetars, some of the most exotic objects in the universe. Magnetars are characterized by extremely intense magnetic fields, producing high-energy electromagnetic radiation. In other words, X-rays and gamma rays. Apart from black holes, nothing in the cosmos generates such magnetic forces. The existence of magnetars was submitted in 1992 by two astronomers, Robert Duncan and Christopher Thompson. They established a relationship between the theory of intense magnetic fields and observations of gamma-ray sources. Observations of neutron stars with high Reynolds numbers, a dimensionless number used in fluid mechanics, demonstrated that these stars could generate extremely intense magnetic fields. While some neutron stars experience an increase in magnetic field strength as their rotational speed decreases, this is not the case for magnetars. This unusual characteristic is actually due to their very structure, and more specifically to their magnetosphere. But before we go any further, how is the magnetic field measured in general? Magnetic flux density is described in Tesla or Gauss units, with 1 Tesla unit corresponding to 10,000 Gauss units. The magnetic field at the Earth's surface corresponds to around 0.5 Gauss. Let's compare a few cosmic objects and their respective magnetic field strengths. The Sun's surface, depending on its activity, emits a magnetic field of around 3,000 Gauss. That of the supermassive black hole Sagittarius A is around 100,000 Gauss. That of the surface of a white dwarf is estimated at 1 million Gauss. Now imagine the strength of a magnetar's magnetic field, which reaches 100,000 billion Gauss at the very least. The magnetic field of any object is constantly changing. According to simulations, a magnetar's magnetic field could occasionally surge to 1 million billion Gauss. When it reaches a certain point between these two variables, it has a considerable impact on the star's outer layers. These, like a protective hyperdense crust as hard as or harder than diamond, see their structure deformed and fractured. When the magnetar's electromagnetic activity intensifies sufficiently, its neutron-based crust vibrates with such colossal intensity that it eventually shatters violently, just as the Earth's crust does during earthquakes. During these stellar tremors, which last between 0.1 and 3 seconds, and follow one another at an inordinate rate, X-rays and gamma rays are produced. These tremors, whose amplitude is estimated at 32 on the Richter scale, provoke veritable explosion eruptions that last a few days, or even weeks, before beginning a gradual decrease in intensity that can last several years before the star returns to its usual luminosity. Magnetars, described as the most powerful magnets in the universe, are the subject of much observation. A joint study by the Institute of High Energy Physics of the Chinese Academy of Sciences and the Kepler Center for Particle Physics and Astrophysics at the University of Tübingen has discovered the magnetar with the strongest surface magnetic field ever observed in the cosmos. The record-holding object is an ultra-bright X-ray magnetar located in the constellation Cassiopeia, 24,000 light-years from Earth. It is the neutron star, swift, J0243, 6 plus 6124, studied thanks to the Swift Multispectral Space Telescope in October 2017. Already known to scientists as the Milky Way's only X-ray source of so-called ultra-bright objects, it is now revealed some of its characteristics, and not the least. It belongs to an X-ray binary system of neutron stars, the other star being a pulsar, which unfortunately is being devoured by its magnetic companion, and with good reason. Its magnetic field is 1.6 billion Tesla, or 16,000 billion Gauss. That's around 5 billion times more intense than the solar magnetic field. Under the effect of this monstrous gravitational force, the gas from the neighboring star has no choice but to fall towards the neutron star, forming an accretion disk. As the plasma in the disk sinks into the magnetic lines until it reaches the surface of the neutron star, it ignites, releasing powerful X-rays. The latter, due to the star's rotation, manifest themselves as periodic X-ray pulsation signals. This is why this type of object is called an X-ray accretion pulsar. By carefully observing the spectrum of these X-rays, scientists discovered an electron-cyclotron absorption line and were able to directly measure the exceptional intensity of the magnetic field. This is the strongest magnetic field ever measured directly in the universe. To date, astronomers have recorded only 31 magnetars. These objects are as fascinating as they are rare. One of them, located around 15,000 light-years from Earth in the constellation Sagittarius, and discovered in March 2020 by the Swift Space Telescope, with rather unusual behavior, is intriguing to scientists. This is Swift J1818.0-1607. Everything suggests that this is the youngest magnetar of all. The primary star is thought to have exploded into a supernova just 240 years ago, around the time of the French Revolution. This conclusion was reached by Australian researchers, who observed the star 8 times between May and October 2020. Initially, they found that its radio emissions were similar to those of a pulsar, with varying intensities. Then these emissions began to behave strangely, sometimes pulsar-like, sometimes magnetar-like. This short-lived phenomenon had never been observed before with any other magnetar. What's more, J1818's magnetic axis is not aligned with its axis of rotation, its magnetic pole being located just below the equator in its southern hemisphere. But that's not the last strange fact. It turns out that on the 1st of August 2020, its radio beam moved briefly at the object's northern hemisphere, suggesting that this star's radio pulses originate from loops of magnetic field lines connecting two closely spaced poles. Typical neutron stars, like our Earth, have north and south poles opposite each other on either side of the object. The observation of this unusual behavior, coupled with the star's data, a mass twice that of the Sun, a diameter of 25 kilometers, and a rotation period of 1.36 seconds, will have enabled astronomers to determine its young age. More common are neutron stars that emit a beam of radiation along their magnetic axis periodically, in the form of very brief pulses. Because this radiation fluctuates or pulses rapidly, a pulsar looks more like a cosmic lighthouse, at least in appearance, than a lambda star or planet, which shine uninterruptedly. Incidentally, for a time, these radio waves, emitted at a rapid and regular rate, were mistaken for manifestations of extraterrestrial civilization. The interval between pulses can range from a few seconds to several milliseconds. If a pulsar also shines continuously, the radiation emitted by each of the two poles of this rapidly rotating star gives the impression of luminosity at regular intervals. Many pulsars cannot be observed from Earth. To be perceived, a pulsar's cone-shaped emission must be directed briefly in our direction. Some 2,700 pulsars have been identified to date, most of them in the Milky Way, some in its star clusters. Only a handful of pulsars have been detected in the Magellanic Clouds. Among the most famous pulsars, we can't ignore the very first to be discovered in 1967 by Jocelyn Bell. It's PSR B1919+21, located in the constellation Little Fox, which we've already observed earlier, just like the Crab pulsar. But let's take a closer look at the different types of pulsar, whose characteristics depend largely on their environment and age. The most common are radio pulsars. These can only be detected in the radio range, thanks to their intense pulsed emission. This is why we no longer speak of stars in the strict sense of the term, but of compact radio sources. X-ray pulsars, on the other hand, are detected by their X-ray emission. This X-ray emission is not related to the surface emission, which is nevertheless very hot, at least several million Kelvin, but is generally the result of an energetic process triggered by the star's rapid rotation. A second theory suggests that these X-ray emissions are due to a colossal energy release, attributed to the accretion of matter from a second object, particularly in binary systems. Other pulsars, known as gamma-ray pulsars, emit, as you'd expect, gamma rays. Around 100 gamma-ray pulsars have been identified to date. Most objects of this type that evolve on their own are as rare as they are difficult to detect. They are usually found in binary systems. Isolated pulsars, whether X-ray or gamma-ray, are virtually all radio pulsars. Some X-ray pulsars are said to be anomalous, as they exhibit abnormally high X-ray emission, resulting in an extraordinarily strong magnetic field. What's more, compared with other pulsars, they have a very long rotation period, of the order of 6 to 12 seconds. They also undergo a very rapid deceleration phase, meaning they are probably very young objects, potentially due to their extreme magnetic field. In contrast, some pulsars have prodigious rotation periods, ranging from 1 to 10 milliseconds. These are the millisecond pulsars, sometimes referred to as recycled pulsars. Their magnetic field is one of the weakest, although close to 100 million Gauss. Often orbiting a companion star or white dwarf, millisecond pulsars are very old. Last but not least, magnetars, the objects with unparalleled magnetic field strengths that we described earlier are also a type of pulsar. Their disconcerting properties have yet to be fully explained. Are they singular objects, or are they just a temporary but usual phase in the evolution of pulsars? Understanding the stages through which stars pass also means being able to estimate their age. But how do scientists go about giving pulsars even an approximate date of birth? As we've just seen, pulsars rotate rapidly on themselves. Knowing that a pulsar's speed of rotation decreases over time due to its electromagnetic radiation, scientists are able to calculate the object's approximate age. Another method is to estimate the pulsar's kinematic age. In this case, after studying the object's immediate environment and defining the location of the supernova, researchers determined the time it took for the object to reach its current position. Many neutron stars have astonishing properties. We've already discussed Swift J818, which turns out to be a magnetar behaving like a pulsar, whose estimated age of just 240 years makes it the youngest pulsar yet discovered in the galaxy. But another pulsar is challenging astrophysicists with its strange behavior. PSR J0901-4046, also discovered in 2020, was detected after one of its pulses was picked up by the Meerkat radio telescope in South Africa. Because of its unusual behavior for a pulsar, it has long remained discrete. Unlike other stars in its class, which rotate at very fast, even dizzying speeds, this one takes an inconceivably slow 75.88 seconds to complete one revolution. The slowest pulsar observed until this discovery completed a revolution in 23.5 seconds. For the researchers, this excessive slowness is more than a little disconcerting, especially as they thought that the radio emissions of neutron stars were a direct consequence of their rapid rotation. Another phenomenon makes this star totally baffling. It emits 7 different types of pulse, each with a different evolutionary history. Astronomers studying this type of star still have countless data to interpret, which should enable them to understand how they form and how they evolve. Above all, this latest find suggests that many stars like this slow pulsar are still hidden in our galaxy. As you know, in the cosmos, stars sometimes come very close together, forming binary systems. Some of these are natural laboratories for studying high-energy physics, general relativity, and stellar evolution. These are X-ray binary stars. These systems are composed of 2 different stars. One is an ordinary star, similar to the Sun, and the other is a neutron star, or in some cases a black hole. The neutron star, or black hole, formed in the aftermath of a supernova, gravitationally attracts matter from its companion star, resulting in intense X-ray emissions. The material falling towards the neutron star forms a compact disk, from which friction generates such heat that a plasma is created, hot and shining in the X-ray range. 2 main types of X-ray binary star have been described. There are transient sources and persistent sources. The former are those that exhibit significant variations in luminosity, while the latter are stable, at least from the point of view of light emission. One of the most extensively studied X-ray binary stars is HER X1. Located in the constellation of Hercules, it is composed of a normal A-type star and a 1.5 solar mass neutron star. The latter gravitationally attracts matter from its companion, forming the inevitable accretion disk that emits X-rays. These very intense rays vary according to several time periods. Because of its rotation, the star pulses with a period of 1.24 seconds. It eclipses every 1.7 days, according to the period of the binary orbit. More importantly, HER X1's disk wobbles every 35 days, its line moving up and down as it rotates. The accretion disk of this neutron star thus has this strange feature. It wobbles as it rotates, influenced by winds within the disk. The study of disk winds fascinates scientists, who remain unsure of their origin. Is it the object's intense magnetic field that breaks up the disk before expelling some of the material outwards in the form of a wind? Or is it the radiation from the neutron star that heats up the surface of the disk, evaporating some of it and sending it flying away like white-hot gusts? Astronomers are working hard to determine the origin of these winds and to understand how they influence their environment. The majority of neutron stars observed to date are part of a binary system. In most cases, their companion is a main sequence star, a white dwarf, a red giant, or even another neutron star. Scientists also suggest that a neutron star could just as well be in close proximity to a black hole. Should such a discovery ever be made, it would be a major breakthrough for astrophysics. In the course of their many observations, radio astronomers at the Parkes Observatory in Australia detected an unusual binary system in May 2003. This relatively close system, located in the constellation of Pope and only 2,400 light-years from Earth, consists of two stars, which up to now has been nothing out of the ordinary. However, in-depth study of this system, named PSR J0737-3039, has revealed two equally sensational features. On the one hand, this system is made up of two pulsars of at least 1.4 solar masses each, a feature that has never been observed in any other system. Secondly, these two components orbit each other at an extremely short distance, estimated at twice the distance separating the Earth from the Moon. In short, these two pulsars, which take it in turns to eclipse each other, remain within a cosmic handkerchief the size of our Sun. These observations were greatly facilitated by the fact that the system's orbital inclination is practically 90 degrees to the Earth, showing us its edge. When the first pulsar is detected, its signal shows a modulation with a period of 2.45 hours. For the researchers, this Doppler effect means that a companion is evolving alongside the pulsar under study at a relatively short distance. This fact is confirmed by the next observation, which describes the two stars as pulsars, the first with an intrinsic rotation period of 23 milliseconds, the second 1,000 times slower, turning on itself in 2.8 seconds. This duo have what it takes to put Einstein's famous theory of general relativity into practice. According to this theory, orbital motion can generate a deformation of space-time, causing the axis of rotation of one of the two components of a binary system to oscillate, a movement known as precession. After 16 years of remarkably precise observations, the measurement of precession analyzed corresponds to the estimates delivered by the equations of Einstein's theory. Predictions of the energy loss associated with gravitational waves have similarly matched the theory. Based on these data, scientists estimate that the common orbit of the two pulsars is shortening by 7 millimeters per day, leading to an inevitable merger, which is expected to occur in around 85 million years. Neutron stars never cease to amaze anyone interested in them. Would you believe me if I told you that such stars host one or more planets? In 1992, the first planet, or rather pulsar planets, were identified by the Arecibo radio telescope on the island of Puerto Rico, the largest single radio telescope in existence until 2016. This discovery was made possible by chronometry, which enables us to measure the minute variations in pulsar periodicity and deduce the main orbital parameters of the objects responsible. The first planetary system discovered evolves around a pulsar in the Virgo constellation, approximately 2,300 light-years from Earth. Named PSR B1257+12, it has been known since 2007 to contain not one, not two, but 3 exoplanets, with a fourth yet to be confirmed, as well as a potential asteroid belt. In 1992, this announcement sent shockwaves through the scientific community, which had thought that planets could only be found near main sequence stars. The closest planet to the pulsar, Quasar, has a mass 50 times less than that of the Earth, and orbits the pulsar in just over 25 days. It is the smallest planet ever observed in the universe. The second, named Poltergeist, is the most massive, with an estimated mass 4.3 times that of the Earth. Farther away, it orbits in 66.5 days. Relatively close to the third planet identified, Phobetor, it is in close gravitational interaction with the latter, which is about 3.9 times more massive than the Earth. Finally, a fourth object has been awaiting confirmation since 1996. An initial study, later refuted, suggested the presence of a planet 100 times more massive than the Earth, and some 40 astronomical units from its star. However, an object does appear to be located in this region of space, causing disturbances to the system under study. For some, it may not be a planet but an asteroid, or even a comet. The second planetary system of this type is located in the constellation Scorpio, more precisely in the globular cluster Messier 4. In this binary system, composed of the pulsar PSR B1612-26 of approximately 1.35 solar masses, and the white dwarf WD B1620-26 of approximately 0.34 solar masses, evolves the Genesis planet, more commonly known as Methuselah. This exoplanet, known as circumbinary because it orbits a binary star, is about 2.5 Jovian masses in size, It takes around 100 years to complete a full orbit around its two stars, but its most spectacular feature is its age. 3 times older than our planet Earth, it could be as much as 13 billion years old. It is undoubtedly the oldest planet ever observed in the history of astronomy. The study of this exoplanet is of great interest to scientists. Formed shortly after the Big Bang, it is thought to be composed essentially of chemical elements, resulting from the primordial nucleosynthesis that took place during the first instance of the universe's life. Neutron stars have extremely varied but relatively stable rotational speeds. There are a few exceptions, however, and they sometimes undergo punctual and sometimes sudden accelerations. Astrophysicists call this phenomenon a glitch. This strange behavior is regularly observed in a neutron star just under 1,000 light-years from Earth. The Vela pulsar, visible in the southern sky, undergoes a glitch approximately every 3 years. Since this rotation anomaly seems to affect only a small population of pulsars, around 5% of them, the Vela pulsar, which experiences this problem with regularity, is particularly popular with glitch hunters. Observing these anomalies has enabled researchers to learn more about the star's composition. They found that at the moment of the glitch, the star began to rotate at a higher speed than previously observed, before slowing down to its cruising speed. They then deduced that the pulsar's center is actually made up of 3 components, one of which is a superfluid neutron soup located beneath the star's crust. Displacements within this hypothetical superfluid core would cause the famous starquake. When this neutron soup collides with the rigid outer crust, the celestial body is accelerated. Then, when a second mass of superfluid from the core hits the first wave, the star's rotation slows down. But these exciting observations raised a new mystery when it was observed that just before the glitch, the neutron star seemed to experience a slight slowdown before regaining speed. As yet, no explanation has been put forward, especially as there is no evidence that this phenomenon is related to the cause of the glitch itself. To understand the inner workings of such a celestial object, we must also consider its formation process. Neutron stars are among the densest celestial bodies in the universe, but knowing that they are merely the remnants of a dead star makes them all the more fascinating. Considered to be the little sisters of black holes, neutron stars can only form from certain stars, which must be particularly massive to make their final bow in a cataclysmic fireworks display known as a supernova. A star at the end of its life, over 10 solar masses, has a great chance of a second life as a neutron star. In other words, a dead star core. It all starts when a massive star reaches the end of its life, having burned all its fuel for the thermonuclear reaction. Some expand into peaceful red giants, but the most massive collapse in on themselves, exploding into a supernova. In this stellar disaster, the outer gaseous layers of the star are expelled into sidereal space. All that remains is the star's core, which no longer has enough energy to sustain the gravitational force. If its mass is less than 1.4 solar masses, it will take the form of a white dwarf. But in our case, its core, between 1.4 and 5.8 solar masses, generates energy in excess of the Chandrasekhar limit. As a result, electrons collide with protons, creating neutrons. The degenerate star eventually stabilizes. The remaining compact residue is then called a neutron star, with an average density corresponding to around 1,000,000 billion times that of water. Neutron stars are therefore born during explosive supernovae. While their future seems rather peaceful once the storm has passed, some of them experience other equally catastrophic events, notably stellar collisions. On August 17, 2017, Canadian astronomers were lucky enough to witness one of the most sought-after events in astrophysics: the explosive merger between two neutron stars. The two stars, located approximately 130 million light-years from Earth in the constellation Hydra, orbited each other at an ever-increasing speed, distorting the surrounding space-time, until the inevitable happened. The two massive stars collided and merged, triggering a gigantic explosion, which, due to its remoteness, could only be observed on this particular day in 2017. The event was first picked up by the LIGO and Virgo gravitational wave detectors in the USA and Italy respectively, and 2 seconds later, NASA's Fermi telescope detected a sudden burst of gamma radiation. For scientists, these two near-simultaneous observations led to a major discovery. For the first time, they were able to observe gravitational waves emitted, not by the merging of two black holes, but by the merging of two neutron stars. The signal detected proved to be much longer than in the case of black hole mergers, around 100 seconds versus a fraction of a second. Their second discovery was that this source of gravitational waves emitted light, which was observed for several weeks by 70 other ground and space-based observatories. This exceptional event, linked to two signals and named GW170817, became the first example of multi-messenger astronomy. For the first time in the history of astrophysics, such a cosmic event could be observed and confirmed using gravitational and electromagnetic waves. Because of its intensity, the explosion was catalogued as a kilonova, the first to have been the subject of real observations. Subsequently, scientists discovered that the new shape created by this fusion between the two neutron stars was, to their great surprise, perfectly spherical, as previous stellar explosion models had suggested a flattened, asymmetrical shape. The observation of this kilonova thus demonstrated that the theories and simulations carried out over the previous 25 years concerning these massive explosions were inaccurate. The error was attributed to the underestimated force of the explosions. Indeed, it was subsequently demonstrated that during the fusion process, the two neutron stars become part stellar giant before gravity causes them to collapse in on themselves. In this short space of time, colossal energy is released by radioactive decay in the star's core, allowing the explosion cloud to take on this unexpected spherical shape. Apart from the space-time undulations observed during this cataclysmic merger between two neutron stars, astrophysicists have made another discovery that should leave you dreaming. The collision of these two exotic stars has finally allowed them to solve the age-old riddle of how elements heavier than iron are synthesized in the universe. Remember, the heaviest element a star seems capable of creating is iron. Yet the cosmos is home to countless small, insignificant objects, at least at first glance, containing much heavier metals, such as silver, gold, and platinum. According to Enrico Ramirez Ruiz of the University of California at Santa Cruz, kilonovae, resulting from the fusion of two neutron stars, could well be the origin of an alchemy that creates these rare metals. According to the scientist, large quantities of neutrons are expelled during the cataclysm. These suddenly accumulate on neighboring heavy nuclei, forming heavier elements in a phenomenon known as the R process, or fast neutron capture. A single collision of this type could generate a colossal quantity of gold, equivalent to, hold on to your hat, a mass comparable to that of Jupiter. I leave it to you to imagine the enormous quantities of these singular atoms that could then sail with the cosmic tides in certain regions of space. As for the gold present on our Earth, it corresponds to the remnants of original gold atoms captured by our planet at the time of its formation, or deposited by asteroids that crashed into its crust. Other mergers between massive objects have been studied, notably that of two black holes whose gravitational waves were observed on September 14, 2015, thanks to the LIGO-Virgo collaboration, confirming the vibrations of space-time predicted 100 years earlier by Albert Einstein. Numerous other similar events have been detected. However, one scenario was missing, that of a mixed collision involving a neutron star and a black hole. Now, in January 2020, astrophysicists were fortunate enough to detect, just 10 days apart, two distinct signals corresponding to this precise pattern of mixed fusion. Again, thanks to the collaboration of LIGO and Virgo, but also KAGRA, the Japanese gravitational wave detector, unusual gravitational wave events were recorded. On January 5, 2020, the signal name GW200105 came from a region of space around 900 million light-years from Earth, followed on the following January 15th by the signal named GW200115, a billion light-years away. Both turned out to be the result of collisions involving a large and a smaller mass, corresponding in both cases to a black hole violently absorbing a neutron star. This extremely rare phenomenon confirmed that beyond theory, a merger of this type could indeed occur. It also led to the conclusion that the neutron star, although highly massive, had been literally swallowed up by the black hole, which made short work of it without leaving the slightest crumb. Now we need to know the history of these two distinct, relatively massive objects. Did they originate from a pair of stars, one of which at the end of its life mutated into a black hole before engulfing its neighbor? Or did these two objects, originating in neighboring regions, eventually see their paths cross until the final explosive encounter? But let's return to a less chaotic region of space. I suggest you discover the neutron stars closest to our Earth. Known as the Magnificent Seven, or the Seven Mercenaries, they were all discovered by the Rosat satellite, a German space telescope designed in the 1990s to observe low-energy soft X-rays. The first of these stars identified in 1992 was confirmed as a neutron star in 1996, followed by the other 6. Located just 390 to 1,630 light-years from Earth, these stars generate powerful magnetic fields, and unlike their middle-aged counterparts, seem to remain extraordinarily quiet, giving off soft X-rays and ultraviolet light. This group of stars is of great interest to astrophysicists. They provide an ideal laboratory for unraveling the mystery of dark matter. Never observed by scientists, we still know nothing about the properties of this matter, for which there is nevertheless substantial astronomical evidence of its existence. For now, science suggests that dark matter could be a stable, electrically neutral subatomic particle of unknown mass. This theoretical particle is incidentally called an axion. Scientists are therefore interested in the Magnificent Seven that emit soft X-rays. Relatively silent and very quiet, these stars represent a unique opportunity to search for small, unexpected bursts of other forms of light, which could be linked to the presence of axions. By interacting with the intense magnetic field enveloping the neutron star, these could be converted into photons, or high-energy X-rays, i.e., hard X-rays. So far, astronomers have revealed that 2 of the 7 stars emit significant amounts of hard X-rays, while the others seem to emit them in much less obvious ways and in varying quantities. This suggests that axions may be the source of these hard X-rays. However, these axions have not been observed. This is still only a hypothesis, which needs to be put into practice. In fact, many laboratories are trying to reproduce this scenario. Who knows? One day soon we'll be told we've solved the mystery of dark matter, not in space, but on Earth. Another fact about the Magnificent Seven cannot be overlooked. It turns out that these neutron stars would have an 8e companion. Discovered in 2007, this neutron star, located in the Little Dipper constellation, at an estimated distance of between 250 and 1,000 light-years, has been christened Calvera. Located outside the galactic plane, its configuration remains a mystery. It is one of the few neutron stars to evolve on its own, with no companions or supernova traces in its vicinity. Could it be the remnant of an exploded star in our galactic disk? Researchers don't yet have an answer, but say it's probably the closest neutron star to Earth known to date. Its proximity and very high X-ray luminosity make it a prime target for studying this type of unusual star. Numerous research programs are underway to determine whether it emits pulses, either in X-rays or in the radio spectrum. Some neutron stars display ever more extraordinary characteristics. This is particularly true of J0740 plus 6620, whose discovery in 2019 has unsettled American astronomers. This pulsar is so massive that scientists thought no such star could exist, This small neutron star, with a diameter of no more than 30 kilometers, or 20 miles, single-handedly defies the laws of physics, boasting a mass of 2.3 solar masses, or 700,000 times that of our Earth. Its mass, calculated thanks to the presence of a white dwarf companion, is so great that the star should be in the process of collapsing into a galactic black hole of several billion solar masses. However, this is not the case. This neutron star, though microscopic on the cosmic scale, should enable researchers to study the limits of stellar mass and further unravel the laws of the universe. One of the most unusual neutron stars is J1008-57. This is an X-ray pulsar in the accretion phase, detected in 1993 by a NASA gamma-ray space observatory. Its strangeness lies in its surface magnetic field, which is the strongest ever detected. It is around 1 billion Tesla, tens of millions of times stronger than a magnetic field that can be created in a laboratory on Earth. This exceptional peculiarity was discovered in 2020 by the Chinese Space Agency, which was quick to share this finding, challenging the known upper threshold of cyclotron resonant scattering. Neutron stars really are the stars of extremes. Although they are among the densest objects in the universe, one of them has once again stumped astronomers with its mass. It has not turned out to be monstrous, but on the contrary, has a value well below that predicted by theory. Named J1731-347, the star appears to be a neutron star in the afterglow of a supernova, 8,150 light-years away, with a mass of just 0.77 solar masses and an estimated radius of 10.4 kilometers, or 6 miles. Until now, the lightest neutron star had a mass equivalent to 1.17 times that of the Sun. This once again challenges our understanding of stellar physics. Scientists are still trying to work out whether this is indeed an extremely light neutron star or a star of quarks. If the former, how could it have formed? Could a large part of its initial mass have been extracted from the core during the explosion due to the presence of its companion? Or could this star actually be a strange star, that hypothetical type of star, very dense and composed essentially of strange quarks of unknown composition? If so, it would be the first star of this type to be discovered. Indeed, strange stars are only a theory at the moment, and would lie on the borderline between a neutron star and a black hole. Finally, we can't look at neutron stars without considering the case of Betelgeuse, the well-known star in the Orion constellation that forms part of the famous Winter Triangle alongside Sirius and Procyon. Admittedly, it's just a red supergiant with an estimated mass of 15 solar masses. But this dying star, located just 530 light-years from our Sun, whose size is equivalent to 700 times our Sun, and whose luminosity places it 10e position after our Sun in the night sky, has been arousing the curiosity of astronomers for many years. It could well be nearing the end of its explosive life. What's more, a significant drop in its brightness was noted at the end of 2019, lasting several months before it returned to its previous appearance. While not all scientists agree on the reasons for this punctual dimming, the fact remains that the star goes through pulsating phases during which its size and luminosity fluctuate. Betelgeuse seems to be showing warning signs that the supernova that will give it the final coup de grace may be just around the corner on a human scale. For some astronomers, Betelgeuse's core must be in the final stages of carbon fusion. Given that this stellar explosion, which must be visible even in broad daylight, will take 530 years to be observable from Earth, it remains to be seen whether we will have the opportunity to admire it in our lifetime. We've now reached our destination. It's time to take a closer look at the local group. The local group is located at the edge of a giant supercluster of galaxies, the Virgo Supercluster. Also known as the local supercluster, the Virgo Supercluster is a supercluster of galaxies comprising the local group, and at its center, the Virgo cluster. It comprises around 10,000 galaxies, and much of its mass is probably dark matter. As the universe expands, the local group is moving away from the Virgo cluster, and therefore from the center of the Virgo supercluster. The local group extends over a diameter of around 10 million light-years. It contains every type of galaxy except giant elliptical galaxies, which are not found in such small structures. That's right, because the local group, despite its 10 million light-year diameter, is not considered a large structure by comparison with other galaxy superclusters. We can't know the exact number of galaxies in the local group. Some are too faint, others are obscured by the Milky Way. Depending on the source, you may hear talk of 60 or 80 galaxies. In any case, there are more than 50. In the local group, there are 3 spiral galaxies: the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Spiral galaxies account for 3/4 of the galaxies listed in Hubble's classification of galaxy types, developed by Edwin Hubble in 1936. Their structure is particularly complex compared to that of elliptical galaxies. Spiral galaxies consist of a flattened disk containing a few hundred billion stars and a luminous spherical central bulge known as the bulge. 2 or more luminous arms extend from the disk, spiraling around the bulge. The center of the disk rotates faster than the edges. Barred spiral galaxies like the Milky Way are distinguished from ordinary spiral galaxies. Barred spiral galaxies have a linear structure instead of 2 spiral arms. Spiral galaxies also contain a lot of gas and dust. The arms of a spiral galaxy are made up of these gases, as well as the youngest and brightest stars. Scientists believe that spiral galaxies have this spiral shape at the beginning of their lives, when they contain a lot of gas, and then gradually lose their rotation and become elliptical as galaxies merge. The local group also contains 2 Magellanic spiral galaxies, the Large Magellanic Cloud and NGC 3109. This type of spiral galaxy has only 1 spiral arm, and is smaller than an ordinary or barred spiral galaxy. Only 1 elliptical galaxy has been identified in the local group, M32, which is a satellite of the Andromeda Galaxy. Elliptical galaxies differ from spiral galaxies primarily by their elliptical shape, but not only. Unlike spiral galaxies, they don't contain a gas disk where young stars can form, and the movement of stars is random, whereas in spiral galaxies, stars are in rotation. Elliptical galaxies are made up of old stars, which is why scientists believe they form when two spiral galaxies collide. In the local group, M110 and NGC 147 are dwarf elliptical galaxies, a type often found in galaxy clusters and often companions to other larger galaxies. The majority of local group galaxies are spheroidal dwarf galaxies, galaxies that are more or less spherical in shape and small in size, i.e., with a few million to a few hundred million stars. Spheroidal dwarf galaxies are ancient and have evolved very little, and their composition resembles that of globular clusters, very dense concentrations of spherical stars orbiting galaxy nuclei. Finally, the rest of the local group are irregular galaxies. These galaxies show no regular structure, being neither spherical, elliptical, nor spiral-shaped. Most irregular galaxies are dwarf galaxies, rich in bright stars and therefore very luminous. Even so, they are difficult to detect because of their small size. Scientists believe that this type of galaxy was once very common in the universe, but that collisions reduced their number. Today it is estimated that at least 10% of all galaxies are irregular. We're now going to take a closer look at each of the main galaxies identified as part of the local group, from the galaxy closest to us to the most distant. The Milky Way, our galaxy, is the second largest galaxy in the local group. It's also known as the galaxy with a capital G. It's a spiral galaxy, home to between 200 and 400 billion stars, including the Sun, and probably over 100 billion planets. The Milky Way's diameter is estimated at 100,000 to 120,000 light-years, perhaps even as much as 200,000 light-years. The center of the galaxy is a supermassive black hole, Sagittarius A, and the solar system is located 27,000 light-years from this center, so it's more on the periphery. Stars revolve around the center of the galaxy, and the Sun takes around 250 light-years to complete a full circle. Since it came into being, the Sun has made only about 20 revolutions. You may be wondering why our galaxy is called the Milky Way. When seen from the sky, the Milky Way looks like a white streak, like a milky flow of stars. In Greek mythology, the origin of the Milky Way is explained in an imaginative way. The Greeks recounted that Zeus had had an illegitimate child, Heracles, with his mistress, Alcmene. Zeus, wishing to make his son immortal, took advantage of a moment when his wife Hera was dozing to lay the infant Heracles on her breast. He begins to suckle Hera, but she wakes up and realizes that this is not her real child. So she forcefully pushes him away, leaving a trail of milk in the sky that will become the Milky Way. The Milky Way has also often been likened to a river. The Egyptians thought it was a copy of the Nile in the sky. The Chinese called it the Silver River, and the Japanese the River of Paradise. This idea of a river in the sky can be found in several Asian mythologies. Lastly, it could also have religious connotations, as was the case with the Mayans, who believed it to be a religious path, enabling souls to reach paradise. In 1610, Galileo was the first to show that the color of the band formed by the Milky Way in the sky was due to the presence of numerous stars. It wasn't until the 1920s, however, that Edwin Hubble proved that the Milky Way was just another galaxy. In the 1930s, the Milky Way's galaxy model was established, a barred spiral galaxy. The Milky Way has 6 spiral arms, which in turn divide into other spiral arms: the arm of Perseus, the arm of the Ruler, the arm of the Swan, the arm of the Cross, the arm of Sagittarius, and the arm of Orion. Our solar system is located in the Orion arm. If the Milky Way appears to us as a flat disk in the sky, it's because we see it from the edge. According to researchers, our galaxy was formed by the merging of several dwarf galaxies that appeared 800,000 million years after the Big Bang, during a phase of very active star formation. There are many different types and ages of stars in our galaxy. In fact, the oldest star in the Milky Way, HE 1523-0901, is 13.2 billion years old, so it appeared shortly after the Big Bang. This is the scenario that has so far been accepted to explain the formation of the Milky Way. 13 billion years ago, 2 galaxies began to form stars independently of each other. On one side was a dwarf galaxy, Gaia Enceladus, and on the other, a galaxy 4 times more massive and richer in metals. 10 billion years ago, these 2 galaxies collided. Some of their stars were ejected into chaotic orbits, forming the Milky Way halo. For 4 billion years, violent episodes of star formation followed one another, until around 6 billion years ago. The remaining gas settled into the Milky Way's disk, which we can still observe today. Surrounding the Milky Way are orbiting dwarf galaxies, including the Small Magellanic Cloud and the Large Magellanic Cloud, which are visible to the naked eye from Earth in the southern hemisphere. The Great Dog dwarf galaxy is the closest known satellite galaxy to us. It is located in the Big Dog constellation, 42,000 light-years from the center of the Milky Way and 25,000 light-years from our solar system. It is an irregular dwarf galaxy and contains 1 billion stars, equivalent to 1% of the Milky Way. It was discovered rather late, in 2003, because it lies behind the plane of the Milky Way, where clouds of gas and dust are denser. However, this galaxy may no longer exist in the future. The tidal forces of the Milky Way are tearing it apart. At present, the center of the Great Dwarf Dog Galaxy is badly degraded, with a long filament of stars trailing behind it, 3 times around the Milky Way. This filament of stars is sometimes referred to as the unicorn ring, and it was this filament that enabled scientists to discover the Great Dwarf Dog Galaxy. Let's continue a little further. 80,000 light-years from Earth and 50,000 light-years from the center of the Milky Way lies the dwarf Sagittarius galaxy. This galaxy is thought to be elliptical or spheroidal, and should not be confused with the irregular Sagittarius dwarf galaxy. In fact, we don't know whether it's spherical or elliptical, as it's being stretched by the tidal forces of the Milky Way. The Sagittarius dwarf galaxy was discovered in 1994. At the time, it was the closest known galaxy to our own. It too is rather difficult to observe, as it is diametrically opposed to the solar system in relation to the center of our galaxy. Spectroscopic analyses have shown that this galaxy is probably very old. It is made up only of old metal-poor stars, known as Population 2. Scientists predict that it will eventually be absorbed by the Milky Way. A little further on, the Large Magellanic Cloud is a barred Magellanic spiral galaxy. With a diameter of 14,000 light-years, it is the fourth most massive galaxy in the group, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. The Magellanic Spiral Galaxy is a type of spiral galaxy with a single spiral arm. This type was coined for the Large Magellanic Cloud by French astronomer Gérard de Vaucouleurs when he revised Hubble's classification. Unlike the other two satellite galaxies we've seen so far, the Large Magellanic Cloud can be seen from Earth, more precisely from the southern hemisphere. In fact, it was discovered much earlier than the Great Dog and Sagittarius dwarf galaxies, since it was first mentioned in 964 by a Persian astronomer by the name of Abd al-Rahman al-Sofi. The Large Magellanic Cloud could collide with the Milky Way long before the Andromeda Galaxy. It is home to some remarkable celestial objects, including the Tarantula Nebula, a region of ionized hydrogen, or HII, and the largest nebula known to date. In this zone, the star birth rate is higher than in any other region of our galaxy. The Large Magellanic Cloud also contains stellar black holes, celestial objects created by the evolution of the most massive stars after their supernova explosion. There's also a soft gamma-ray star, SGR 0526-66, a source of gamma rays that is probably linked to young neutron stars with strong magnetic fields. The Large Magellanic Cloud is linked to the Small Magellanic Cloud by a bridge of gas and stars called the Magellanic Bridge. The Small Magellanic Cloud is an irregular galaxy located in the Toucan constellation and is one of the most distant celestial objects visible to the naked eye. However, like the Large Magellanic Cloud, with which it forms a pair, you can only see it from the southern hemisphere, far from light pollution. Like the Large Magellanic Cloud, the Small Cloud was first mentioned by navigator Amerigo Vespucci in a voyage report from 1503 to 1504, but it was Magellan's expedition that gave it its name. The Small Magellanic Cloud is thought to have been a barred spiral galaxy, distorted by the tidal forces of the Milky Way. The Bouvier dwarf galaxy lies close to both Magellanic Clouds. We are now 195,000 light-years from the Sun. This spheroidal dwarf galaxy is located in the constellation du Bouvier, hence its name, and was discovered in 2006. Its luminosity is estimated at 100,000 times that of the Sun, which is very low for a galaxy. The Bouvier dwarf galaxy is strongly disrupted by the tidal forces of the Milky Way. It is composed mainly of very old stars, aged between 13.3 and 13.4 billion years. Let's continue our journey to discover the Milky Way's satellite galaxies. Just 205,000 light-years from our solar system lies the Little Dipper dwarf galaxy, a spheroidal galaxy, located, as you may have guessed, in the Little Dipper constellation. This galaxy was discovered in 1955, thanks to a photographic survey of the night sky carried out at the Palomar Observatory, 80 kilometers north of San Diego, California. Like almost all of the Milky Way's dwarf satellite galaxies, the Little Dipper dwarf galaxy is essentially composed of old stars with little interstellar matter. A little further away, 260,000 light-years from us in the constellation of the Dragon, the dwarf Dragon galaxy was also discovered, thanks to photographic surveys by the Palomar Observatory. This spheroidal dwarf galaxy is one of the least visible satellite galaxies because it is so faint. "280,000 light-years away, the sextant dwarf galaxy is a spheroidal dwarf galaxy discovered in 1990. It too is not very luminous and is one of the least luminous nearby galaxies. Just next door, 285,000 light-years away, the Sculptor dwarf galaxy was the first spheroidal dwarf galaxy in 1937. Analysis of its composition has revealed that it is similar to the primitive galaxies observed at the edge of the universe. Let's continue a little further afield. There are still more satellites of the Milky Way to observe. The Carina dwarf galaxy, 330,000 light-years away, is a spheroidal dwarf galaxy that formed a little more recently than the others. Most of its stars are thought to have formed 7 billion years ago, although analyses have also revealed periods of star formation as far back as 13 billion years ago, and as recently as 3 billion years ago. This galaxy was discovered in 1977 and is around 75 times smaller than our own galaxy, with a diameter of 1,600 light-years. It is moving away from the Milky Way at a speed of 230 kilometers or 140 miles per second. Recently discovered in 2018, the dwarf galaxy Antlia 2 is located 422,000 light-years from us. As you can see, its size is relatively close to that of the Large Magellanic Cloud, but its luminosity is 10,000 times fainter. In fact, it's the least luminous galaxy ever discovered. That's certainly why it was only discovered late in 2018, when most of the galaxies in the local group were already known at the end of the 20th century. The Furnace dwarf galaxy is located around 450,000 light-years from us. It is also a spheroidal dwarf galaxy, composed of ancient stars, and shines faintly. Several globular clusters have been detected, including NGC 1049, which is brighter than the galaxy itself. NGC 1049 was discovered a century before the Furnace dwarf galaxy. Let's move on a little further to observe the Lion 2 galaxy 700,000 light-years away and the Lion 1 galaxy 800,000 light-years away. Both are spheroidal dwarf galaxies. The Leo 1 galaxy is remarkable for containing very little dark matter, compared with the Milky Way's other satellite galaxies. In 2021, a supermassive black hole of 3.3 million solar masses was discovered at its center. We've now arrived at the Milky Way's last satellite galaxy, the Phoenix dwarf galaxy. Scientists don't know whether this is a spheroidal dwarf galaxy or an irregular one. Perhaps that's why, when it was discovered in 1976, it was classified as a globular cluster, only to realize a year later that it was in fact a galaxy. This short tour of the Milky Way's satellite galaxies would not be complete without mentioning the Lion A galaxy, located 2.25 million light-years from us. The problem is that we don't really know whether the Lion A galaxy is a satellite of the Milky Way or belongs to the group of galaxies known as Antlia sextans. We'll be looking at this group of galaxies a little later in the trip, as it's located even further out on the periphery of the local group. Let's continue our journey towards the other galaxies of the local group. We're now 1.63 million light-years from the Milky Way, in front of Barnard's galaxy, or NGC 6822. This galaxy is a barred irregular galaxy. Simply put, it's the irregular version of a barred spiral galaxy like the Milky Way. Barnard's galaxy was so named because it was discovered in 1881 by the American astronomer Edward Emerson Barnard, who also gave his name to Barnard's star. The Barnard galaxy contains only around 10 million stars, most of them young. Edwin Hubble identified 15 variable stars in this galaxy. Variable stars are stars whose luminosity varies over shorter or longer periods of time. The Sun, on the other hand, is almost constant in brightness, varying by 0.1% over an 11-year cycle. Today, over 150 HII regions have been identified in this galaxy. Previously, it was thought that the universe stopped at 300,000 light-years. The discovery of Barnard's galaxy brought home the true size of the universe. We are now approaching the Andromeda Galaxy, the largest galaxy in the local group, with a diameter of 220,000 light-years. This spiral galaxy is also known as NGC 224, or M31, in the Messier catalog of nebulae and star clusters. This catalog, drawn up in 1774 by French astronomer Charles Messier, was intended to help comet hunters avoid confusing comets with diffuse objects such as nebulae or star clusters. The Andromeda Galaxy is located 2.55 million light-years from the Sun in the Andromeda constellation. Until the 1920s, it was thought to be a nebula rather than a galaxy. It is thought to contain around 1,000 billion stars, 2 to 5 times more than our own galaxy. Its total luminosity would be 26 billion times that of the Sun, or 25% more than our galaxy. But the Milky Way's star formation rate is 3 to 5 times higher than that of the Andromeda Galaxy, and there are twice as many supernovas in our galaxy. Perhaps one day, the Milky Way's luminosity will exceed that of the Andromeda Galaxy. Because it's so luminous, the Andromeda Galaxy is one of the few galaxies you'll be able to observe with the naked eye in the northern hemisphere. If you look carefully, you can't miss it. Its apparent diameter is 6 times the apparent diameter of the Moon from the Earth. In fact, it was discovered a long time ago. The first known written mention of this galaxy dates back to 964 by Abd al-Rahman al-Sofi in his Book of Fixed Stars. However, it wasn't until 1612 that it was observed through a telescope by the German astronomer Simon Marius, the same man who named Jupiter's 4 main satellites, the Galilean moons. The Andromeda Galaxy was first photographed in 1887 by British astronomer and pioneer of nebula photography Isaac Roberts. The Andromeda Galaxy is thought to have formed recently. For astronomers, this means less than 3 billion years ago. At the time it formed, the Earth certainly already existed. The Andromeda Galaxy is thought to be the result of the collision of 2 galaxies. Like the Milky Way, it contains a supermassive black hole at its center, called M31. In around 4.5 billion years' time, an observer on Earth will be able to see the Andromeda Galaxy in the night sky as a pinkish cloud of dust. This is because the Andromeda Galaxy and the Milky Way are about to collide. This collision will have many effects. Firstly, it will cause the collapse of the galaxy's gas clouds. Secondly, it will give rise to new stars. Some stars will be sucked into the black hole, while others will be ejected into intergalactic space. The galaxies, for their part, will merge to form a large elliptical galaxy. Their two supermassive black holes will also merge to form an even larger black hole. Around the Andromeda Galaxy, there are also satellite galaxies like those around the Milky Way. The most important of these is the Triangulum Galaxy, or M33, which is the third most massive galaxy in the local group, with a mass 60 billion times that of the Sun. It is also a spiral galaxy. Perhaps you've already heard of this galaxy, home to the fictional planet Vinea in the science fiction comic strip Yokosuno, and the planet Ganesha in Jean-Gaston Vandel's futuristic trilogy. In reality, we don't really know whether the Triangulum Galaxy is a satellite of the Andromeda Galaxy, but we assume it is. The two galaxies are separated by a distance of 750,000 light-years. We are now some 3 million light-years from our solar system. Although the Triangulum Galaxy was first catalogued by Charles Messier in his catalogue as M33, it had probably been observed before. Under the right conditions, you can even observe it with the naked eye from Earth, more precisely from the southern hemisphere. In fact, mentions of this object have been found as far back as 1850. The Triangulum Galaxy is a regular, unbarred spiral galaxy, but it does have a bar running 2,600 light-years through its center. At the heart of this galaxy is not a supermassive black hole, but an HII region containing an ultra-luminous X-ray source. ULXs are still enigmatic objects for science. What we do know is that they are ultra-powerful X-ray sources. In fact, the ultra-luminous X-ray source in the Triangulum Galaxy is the most powerful X-ray source in the local group. The Triangulum Galaxy is home to other remarkable celestial objects, starting with several HII regions, the brightest of which, NGC 604, may have undergone a burst of star formation as recently as 3 million years ago. 54 globular clusters have been identified around the Triangulum Galaxy, but there are certainly more than double that number. At equal distance from the Triangulum Galaxy and the Andromeda Galaxy, 2.5 million light-years from us, you can see the Pisces Dwarf Galaxy, or LGS-3. This galaxy could be a satellite of the Andromeda Galaxy or the Triangulum Galaxy, if the latter is not a companion of the Andromeda Galaxy. This irregular dwarf galaxy was discovered in October 1978 in a search for satellite galaxies of M31 and M33. 5 objects were cataloged and grouped together under the name Local Group Suspect, hence the name LGS-3. The Pisces Dwarf Galaxy was the only one of the 5 objects to be confirmed as a local group galaxy. The Pisces Dwarf Galaxy contains old, metal-poor stars, but also atomic hydrogen gas, which may indicate the presence of young stars. It may therefore be a transitional object between a spheroidal dwarf galaxy and an irregular dwarf galaxy. What interests scientists about this small galaxy is the presence of a high-speed cloud, called HVC, 127-41-330. In this high-speed cloud, which is probably gravitationally interacting with the Pisces dwarf galaxy, no stars have been detected. And yet, it has a diameter of 20,000 light-years. What's more, HVC 127-41-330 could be 80% dark matter. So, according to American astronomer Josh Simon, it could be the first dark galaxy observed in the universe. A dark galaxy is a hypothetical type of galaxy that is devoid of stars, or at least produces very few of them. If their existence is confirmed, these galaxies would be extremely difficult to detect, as they would be totally obscure. Theoretical models of galaxy formation suggest that dark galaxies are the first stage in the long process of galaxy formation. Observing one would be a giant step towards understanding the formation of our own galaxy. Although the Andromeda Galaxy's satellite galaxies, a dozen or so, are, like the Pisces dwarf galaxy, closer to us than the Andromeda Galaxy itself. Let's start with NGC 185, a spheroidal dwarf galaxy that you'll also see under the name Caldwell 18. Discovered in 1787 and recognized as a member of the local group in 1944, this galaxy is located 2.1 million light-years from us in the constellation Cassiopeia. It appears to be gravitationally linked to NGC 147, or Caldwell 17, another spheroidal dwarf galaxy and companion of the Andromeda Galaxy. The two form a stable binary system. At the same distance from the Andromeda Galaxy as the Triangulum Galaxy is the irregular dwarf galaxy IC10. Located 2.15 million light-years from us, it belongs to the Cassiopeia constellation. Discovered as a celestial object in 1889, it was not identified as a galaxy until 1935. It was Edwin Hubble once again who hypothesized that it belonged to the local group. This was confirmed in 1966 by the measurement of its radial velocity. Smaller than the Small Magellanic Cloud, it is nevertheless as luminous as that galaxy. Its active star-forming phase lasts longer than that of the Small Magellanic Cloud, so there are several generations of stars in this galaxy. On the other hand, it is rapidly consuming its reserves of interstellar gas, which will certainly be exhausted in just a few billion years. This galaxy continues to amaze scientists, as it is also home to one of the most massive stellar black holes known, with a mass several dozen times that of the Sun. Around 2.3 million light-years away, we also find the Andromeda II galaxy, a spheroidal dwarf galaxy discovered in 1972, along with other galaxies named Andromeda 1, Andromeda 3, and Andromeda 4. Like the Pisces dwarf galaxy, Andromeda 2 is located between M31 and M33, so it's not clear which galaxy it's a satellite of, but scientists are leaning towards the Andromeda galaxy. Andromeda 3, 2.5 million light-years away, is also a spheroidal dwarf galaxy. No stars are thought to be forming in this galaxy, as it contains only old stars, either the same age as those in the Milky Way, or some 3 billion years younger. On the other hand, 56 variable stars have been identified. Irregular dwarf galaxy IC 1613, located roughly between Andromeda 2 and Andromeda 3 in the Cetus constellation, has the shape of a spiral galaxy, but the characteristics of both irregular and spheroidal galaxies. It contains very little cosmic dust, making it easy for astronomers to probe its contents. On the other hand, it is very dim, so you won't be able to observe it with the naked eye. We're still 2.5 million light-years away. You can also see the Andromeda 7 galaxy, also known as the Cassiopeia spheroidal dwarf galaxy, which was discovered in 1998. This galaxy is interesting because it is the brightest and most massive of all the spheroidal dwarf galaxies that are satellites of the Andromeda galaxy. It also has the highest metallicity. Its stars are rather old, with 90% of them having formed 5 billion years ago. Not far away is M32, or NGC 221, an elliptical galaxy that is also made up mainly of old stars and has therefore not experienced a period of star formation for a long time. Scientists believe that M32 was originally a spiral galaxy that crossed the galactic disk of the Andromeda galaxy. It would then have lost most of its peripheral mass. It shows signs of a supermassive black hole at its center. Also nearby is the Whale dwarf galaxy, a low-brightness galaxy, like most spheroidal dwarf galaxies. However, it is not a satellite of the Andromeda galaxy. Indeed, this galaxy is too far away to be a satellite, so it's referred to as an isolated spheroidal dwarf galaxy. These galaxies are quite rare in the local group, but the Whale dwarf galaxy is not the only one. The Toucan dwarf galaxy, for example, is also an isolated spheroidal dwarf galaxy. Analyses carried out with a Hubble telescope have enabled scientists to establish that for 8 billion years, there has been no star formation in this galaxy. Four other satellite galaxies of the Andromeda galaxy are located further away from us than M31. These are Andromeda 1, Andromeda 5, M110, and Andromeda 6. Andromeda 1 was discovered at the same time as Andromeda 2, 3, and 4. This spheroidal dwarf galaxy is located 2.6 million light-years from us, and 150,000 light-years from the Andromeda galaxy. It is the least luminous galaxy, in which a globular cluster has been found. Andromeda 5 was discovered 25 years after the first four Andromeda galaxies. It is an unremarkable dwarf spheroidal galaxy, except for its high metallicity. M110, or NGC 205, 2.7 million light-years away, is more interesting to scientists. This elliptical galaxy contains unusual levels of molecular and ionized gas and dust. What's more, its stars follow random motions, while the galaxy itself is animated by a rotational motion. Several globular clusters have been detected in this galaxy, all of which contain old stars, except the one near the galaxy's heart. The last satellite of the Andromeda galaxy, Andromeda 6, also known as the Pegasus spheroidal dwarf galaxy, is thought to be located 3.1 million light-years from M31, and not 2.7 million light-years away, as has long been thought. It should not be confused with the irregular Pegasus dwarf galaxy, DDO 216, which is also a satellite of M31 in the Pegasus constellation. Let's go back a little further to 2.8 million light-years away, where we find the Toucan dwarf galaxy we mentioned earlier. This spheroidal dwarf galaxy is unusual in that it is neither a satellite of the Milky Way nor of the Andromeda Galaxy, like the Whale dwarf galaxy. What intrigues scientists is that it lies almost opposite the other members of the local group in relation to the Milky Way. Unlike other isolated spheroidal dwarf galaxies, the Toucan galaxy is not currently undergoing a period of star formation. In fact, this galaxy appears to be gas-free. It is thought to have been star-forming for around 1 billion years, 13 billion years ago. For the last 8 billion years, no new stars have formed. In fact, the Toucan galaxy is thought to have approached the Andromeda Galaxy around 11 billion years ago, ejecting it far out to its present position. Such galaxies are known as counter-current galaxies. "3 million light-years away, the Wolf-Lundmark Melot WLM galaxy is an irregular barred dwarf galaxy that is not a satellite of either the Milky Way or the Andromeda Galaxy. It is located in the Whale constellation. It had already been observed in 1909 by German astronomer Max Wolf, but was not classified as a galaxy until 1926 by Swedish astronomer Knut Lundmark and British astronomer Philbert Jacques Melot, hence its name. Half of the stars in the WLM galaxy are over 9 billion years old. However, between 1 and 2.5 billion years ago, star formation resumed, particularly in the bar, so there are also young stars in this galaxy. Stars are currently forming in this galaxy. Because it lies at the edge of the local group, the Wolf-Lundmark Melot galaxy has been relatively protected from mergers and interactions with other galaxies, making it an interesting one to study. The dwarf Aquarius galaxy, also known as DDO 210, is another isolated irregular galaxy, located 3.3 million light-years from us. It is in fact part of a group of irregular galaxies that do not appear to belong to any particular subgroup. This galaxy is of interest to scientists because it shows a blue shift. The blue shift is different from the red shift, which you've probably heard of. In a nutshell, the red shift is the spectral evidence emitted by celestial objects that are moving away, such as galaxies, but also planets. Redshift is one of the evidences of the expansion of the universe. Well, the blue shift is the opposite phenomenon. The blue shift is spectral evidence that objects are moving closer to us. The Andromeda Galaxy, which is approaching us and will collide with the Milky Way in a little over 4 billion years' time, shows a blue shift. The same applies to the dwarf Aquarius galaxy. It is approaching our solar system at a speed of 137 kilometers per second, or 185 miles per second. The dwarf Aquarius galaxy is one of the few local group galaxies for which we can rule out a past proximity to the Milky Way, or M31. In other words, based on its current position and velocity, scientists have deduced that it has not in the past been located close to one of the two most massive galaxies in the local group. Like the Wolf-Lundmark Melot galaxy, the dwarf Aquarius galaxy still contains significant quantities of hydrogen, enabling it to support star formation, albeit at a relatively low level. The median age of stars in this galaxy is 6.8 billion years. This makes it the galaxy in the local group with the youngest median age of stars, after the Leo A galaxy. For this reason, scientists have speculated that the late star formation may be linked to the galaxy's isolation. Do you remember that we observed the Sagittarius dwarf galaxy earlier on this trip? This satellite galaxy of the Milky Way is the second closest to us, after the Big Dog galaxy. We're now looking at the irregular dwarf Sagittarius galaxy, not to be confused. The first, 80,000 light-years away, is elliptical or spheroidal. The second is irregular and lies 4.2 million light-years from us, i.e., very close to the borders of the local group. In short, one is very close to us, the other very far away. The irregular Sagittarius dwarf galaxy was discovered in 1977. As it is very close to the local group boundary, we don't really know for sure whether it belongs to this group of galaxies. In any case, if it does belong to the local group as we assume, it's the farthest local group member galaxy from its center of gravity. Far more luminous than the dwarf Aquarius galaxy we've just observed, it would have experienced a longer period of star formation and possesses a large number of intermediate-age stars. Most of the stars in this galaxy would therefore be between 4 and 8 billion years old. Just 4.2 million light-years away, another galaxy is located on the outskirts of the local group in the Big Dipper constellation, UGC 4879. This is one of the most isolated galaxies in the local group. It is an irregular dwarf galaxy. It is separated from its nearest neighbor, the Leo A galaxy, by 2.3 million light-years, the distance between the Milky Way and the Andromeda galaxy. It would seem, however, that this galaxy is getting closer to us. UGC 4879 behaves strangely, intriguing astronomers. The vast majority of its stars formed during the first 4 billion years after the Big Bang. Nothing happened for the next 9 billion years until fairly recently, when star formation resumed. In any case, analyses of this isolated galaxy have shown that it probably contains dark matter and a stellar disk. This solitary galaxy has not interacted with other galaxies, making it particularly interesting material for astronomers seeking to understand the complexity of star birth in the universe. When we were looking at the Lion A galaxy earlier in this journey, we mentioned the Antlia Sextans group. Now that our journey is drawing to a close, it's time to take a closer look. The Antlia Sextans group is a small group of galaxies located in the Hydra, Sextans, Leo, and Pneumatic Machine constellations. On average, it lies 4.3 million light-years from us, at the very edge of the local group. For this reason, this group of galaxies is sometimes considered to be outside the local group. Many researchers say that the Antlia Sextans group is an independent group. This group of galaxies includes NGC 3109, the Sextant A and B galaxies, the Leo P galaxy, and the Pneumatic Machine dwarf galaxy. Let's start with NGC 3109. This small, barred Magellanic spiral galaxy, 24,000 light-years across, is located in the Hydra constellation, some 4.35 million light-years from us. It's a so-called low-surface brightness galaxy, meaning that seen from Earth, its brightness is less than 1 magnitude lower than that of the night sky. So far, so good. Most dwarf galaxies are low-surface brightness galaxies. NGC 3109 does, however, have some original features. It has a very low metallicity, like the Small Magellanic Cloud, and contains an unusually high number of planetary nebulae for its low luminosity. A planetary nebula, which is in fact nothing like a planet, is a large cloud of gas created by a giant star at the end of its life, which becomes unstable and starts ejecting its upper layers. Planetary nebulae are magnificent celestial objects with beautiful colors. Analysis of the radial velocity of the disk deformation of galaxy NGC 3109 has shown that this galaxy and the dwarf pneumatic machine galaxy came closer together around 1 billion years ago. These two galaxies of the Antlia Sextans group are thought to be in a tidal gravitational interaction. The pneumatic machine dwarf galaxy is located 4.17 million light-years from us in the constellation of the pneumatic machine, as its name suggests. It is sometimes classified as a spheroidal dwarf galaxy, sometimes as a spheroidal to irregular transitional dwarf galaxy, and sometimes as an elliptical dwarf galaxy. It contains stars of varying ages, with the youngest concentrated in the center and the oldest on the periphery. The Antlia Sextans group also includes the Sextant A galaxy, an irregular galaxy 5,000 light-years across with a distinctive square shape. At least it's the square shape it appears to us from Earth. The Sextant B galaxy, which forms a pair with the Sextant A galaxy, is also an irregular galaxy. It lies just outside what is considered the boundary of the local group, and is moving away from the Milky Way at a speed of 300 kilometers per second, or 186 miles per second. It is one of the smallest galaxies in which planetary nebulae have been observed. At least 5 have been identified. Finally, the Leo P galaxy is a small irregular galaxy in the constellation Leo. It is very distant, around 5.3 million light-years from us. When it was discovered in 2005, scientists thought it was a high-speed cloud. It wasn't until 2013 that its nature as a dwarf galaxy was confirmed. The Leo P galaxy is home to one of the most metal-poor environments in the local universe, with a very low metallicity of just 3% that of the Sun, and stars containing 30 times fewer heavy elements than the Sun. In fact, the Leo P galaxy is similar to primitive galaxies. It is one of the smallest and faintest star-forming galaxies in the local group, with a total luminosity 440,000 times less than that of the Sun, and a stellar mass only 560,000 times that of the Sun, which is low. It therefore contains relatively few stars. And yet, it's one of the few galaxies in the local group, or in its immediate vicinity, if you consider that it's not part of it, that is currently still forming stars. Does that surprise you? The truth is, its star formation rate is very slow, equivalent to 1 solar mass every 20,400 years. No wonder then that it contains so few stars, even though it has been forming stars steadily for at least 4 billion years. We've now completed our tour of local group galaxies. However, it's important to remember that the local group isn't all galaxies and stars. Let's explore the local group's remarkable objects. Let's start with the Smith cloud. Does the name ring a bell? It's a high-velocity gas cloud with a mass 1,000,000 times that of the Sun. High-speed gas clouds like the Smith cloud are of vital importance in the local group. When they fall into the disk of a galaxy, they add baryonic matter to the already diluted matter present in the disk. Baryonic matter is made up of composite particles known as baryons. More concretely, baryons are the electrons and protons that make up the atoms of all observable molecules and structures in the universe. Stars, for example, are made up of baryonic matter. You can see where we're going with this. High-speed clouds, by adding matter essential for star formation to galaxy disks, will help maintain the galaxy's star formation rate. The Smith cloud is traveling at 870,000 kilometers per hour, or 540,000 miles per hour, towards the Milky Way. It is therefore expected to collide with our galaxy in around 27 million years' time, well before the predicted collision with the Andromeda galaxy. This impact could trigger an explosion of star formation. The most recent studies of the Smith cloud suggest that it formed on the periphery of the Milky Way before being ejected some 70 million years ago. But scientists still don't know how this happened. The Magellanic Current is another notable high-speed cloud of the local group. This is the matter bridge in the wake of the large and small Magellanic Clouds. It moves at a speed of 400 kilometers per second, or 250 miles per second, well above the speed at which our galaxy is moving. We don't really know how it formed, but it's assumed that tidal forces between the Milky Way's two satellite galaxies are behind it. In 2010, it was established that it would cover a distance of 600,000 light-years, which is much longer than researchers had previously thought. From this information, scientists have deduced that the Magellanic Current may have formed around 2.5 billion years ago, when the Magellanic Clouds passed close to each other. The Magellanic Current is of interest to scientists who study it to better understand the interaction of high-speed clouds and our galaxy. Before ending this journey, let's take a look at one last unusual local group object, known as the Unicorn Ring, or Unicorn Current. We already caught a glimpse of it earlier during our exploration of the Big Dog Galaxy. This long filament of stars discovered in 2002 surrounds the Milky Way over a length of 200,000 light-years at a distance of around 53,800 light-years. We don't really know the origin of the Unicorn Ring. It could be the remnants of the merger of two galaxies, either the merger of the dwarf Great Dog Galaxy with the Milky Way, or the merger of the dwarf Sagittarius Galaxy with our own. In any case, according to a 2011 publication in the respected journal Nature, the merger of the Milky Way and the Sagittarius Dwarf Galaxy could create such rings. Another hypothesis asserts that the Unicorn Ring is not actually a ring, but simply an overdensity. Overdensities are said to be common in galaxies with distorted flaring disks, such as the Milky Way. In other words, this is not an independent structure, but a ripple in our galaxy's disk. This hypothesis was invalidated by observations made by the Anglo-Australian telescope in 2007. According to these observations, A deformed disk could not create the structure we observe. For that to happen, the disk would have to erupt, or the cause could be external to our galaxy. In short, we don't know much more at present, but scientists are continuing to investigate the origins of this original local group structure. Our journey is drawing to a close. It's tempting to explore the universe even further. You're probably wondering what lies beyond the local group. Our neighboring galactic group is the IC342 Maffei group, which has the same structure as the local group. In other words, it's made up of two structures organized around massive galaxies. The first is IC342, or Caldwell 5, an intermediate spiral galaxy in the Giraffe constellation, 11.4 million light-years from us. The second is actually a pair of galaxies, Maffei 1 and Maffei 2, both located in the Cassiopeia constellation. Each of these two structures has 9 known satellite galaxies. Like the local group, the IC342 Maffei group is part of the Virgo Supercluster. The local group and the IC342 Maffei group are only a tiny part of our universe. There are many other groups, such as Stephan's Quintet, a group of 5 galaxies located in the Pegasus constellation and remarkably photographed by the James Webb Telescope, or Robert's Quartet, a group of 4 galaxies in the Phoenix constellation. And in a few billion years' time, all this will have changed again. The dynamics of the local group itself are changing, albeit on such a large timescale that we don't realize it. With the merger of its 2 main galaxies, the local group will look decidedly different in 4 billion years' time. In place of the 2 substructures of our galaxy group, we'll have a large elliptical galaxy, whose other nearby galaxies, notably the Triangulum galaxy, will become satellites. It's also possible that the local group will one day merge with the Virgo cluster, the nearest large cluster of galaxies. But we're talking here about a future where the Earth will probably no longer exist, devoured by our sun, then transformed into a red giant. In the meantime, we have plenty of time to continue observing the local group and its surroundings, and to learn a little more every day about the universe and its formation.